In the vast expanse of space, among countless stars and galaxies, we find ourselves on a tiny blue planet, looking outward with wonder and curiosity. For millennia, humanity has gazed at the night sky, trying to make sense of our place in the cosmos. But how much do we truly know about the universe that surrounds us? The answer, perhaps surprisingly to some, is both extraordinary and humbling. We have learned so much, yet our knowledge represents merely a fraction of the cosmic mysteries that remain. Our ancient ancestors crafted elaborate mythologies to explain the heavens. The Babylonians saw the movements of celestial bodies as the activities of their gods. Ancient Egyptians aligned their pyramids with astonishing precision to match celestial coordinates. Greek astronomers like Ptolemy developed complex mathematical models with Earth at the center of creation. The Mayans created sophisticated calendars based on their observations of Venus and other planets. Indigenous cultures worldwide identified constellations as heroes, animals, and legends etched in the night sky. They saw the Milky Way variously as a river, a path, or a celestial serpent. Eclipses were interpreted as omens of doom or blessing, while comets were harbingers of great change. These early cosmologies placed Earth at the center of creation, with crystalline spheres carrying planets and stars in perfect circular orbits. The journey from these ancient perceptions to our current understanding spans thousands of years of human inquiry. The Copernican revolution in the 16th century first dislodged Earth from the center of the universe, placing the Sun there instead. Galileo's telescope revealed mountains on the Moon, rings around Saturn, and moons orbiting Jupiter, evidence that celestial bodies were not perfect divine spheres, but worlds potentially similar to our own. Newton's laws of motion and gravity unified terrestrial and celestial physics, showing that the same forces that caused an apple to fall also kept the Moon in orbit. Each discovery built upon previous knowledge, gradually expanding our cosmic perspective. Modern astronomy has revealed a universe of staggering scale and complexity that would be utterly incomprehensible to our ancestors. We now know that our Sun is but one of hundreds of billions of stars in the Milky Way galaxy, which itself is one among perhaps 2 trillion galaxies scattered throughout the observable universe. The cosmos stretches at least 93 billion light-years in diameter, a span so vast that light, traveling at 300,000 kilometers per second, takes billions of years to cross it. This vast expanse has been expanding ever outward from the moment of the Big Bang some 13.8 billion years ago. The numbers are so large they challenge human comprehension. Our home galaxy alone contains more stars than there are grains of sand on all Earth's beaches combined. Yet for all our progress, the sobering truth is that we've barely begun to understand the universe. The observable universe, that portion of space from which light has had time to reach us since the Big Bang, represents only a fraction of what exists. Beyond our cosmic horizon lies territory forever hidden from our view, unreachable by any telescope no matter how powerful. Light from these distant regions simply hasn't had time to reach us in the 13.8 billion years since the universe began. And due to the accelerating expansion of space, some regions never will make contact with our observable bubble of the cosmos. Perhaps even more humbling is this reality. Of the observable universe, we comprehend remarkably little. Ordinary matter, the stuff of stars, planets, and living things, everything composed of protons, neutrons, and electrons, constitutes a mere 5% of the cosmic inventory. This means that everything we've ever observed with our telescopes, everything we've sent spacecraft to explore, every element on the periodic table, every object that emits or absorbs light, represents just 1/20th of what's out there. The rest, a cosmic mystery, composed of invisible dark matter, about 27%, and an even more enigmatic force called dark energy, roughly 68%. We can detect their effects, but cannot directly observe or fully explain them. It's as if we're trying to understand the ocean by studying only the foam on its waves. Our ignorance extends beyond these invisible components. we still cannot answer fundamental questions that have profound implications for our understanding of reality. What triggered the Big Bang? Was there something before it? What exactly happened in the first fraction of a second after the universe began? Why does the universe contain matter but very little antimatter? Will the universe expand forever or eventually collapse? Are the laws of physics the same throughout the cosmos? Are there other universes beyond our own? Could life exist elsewhere? And if so, how common is it? Is time constant throughout the cosmos? Or could it flow differently in different regions? The list of unknowns seems to grow with each new discovery. Consider the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space. First detected accidentally in 1965, this faint radiation has provided crucial insights into the early universe. Yet it also presents puzzles, like the existence of large-scale structures that shouldn't have had time to form given our understanding of cosmic evolution. Similarly, the accelerating expansion of the universe, discovered in 1998, forced astronomers to postulate the existence of dark energy, a previously unknown force working against gravity on the largest scales. Each answer seems to yield two new questions. Despite these limitations, humanity has developed remarkable tools to probe the cosmos. Ground-based observatories with mirrors spanning dozens of meters can detect galaxies billions of light years away. The extremely large telescope, currently under construction in Chile, will feature a primary mirror 39 meters in diameter, allowing astronomers to study the atmospheres of exoplanets and observe the first stars and galaxies that formed after the Big Bang. Space telescopes like Hubble, launched in 1990, and James Webb, deployed in 2021, peer into the depths of space and time, capturing light from the universe's infancy without the distorting effects of Earth's atmosphere. Radio telescopes like the Square Kilometre Array will listen for signals from distant celestial objects with unprecedented sensitivity. Particle accelerators like the Large Hadron Collider recreate conditions that existed fractions of a second after the Big Bang. Gravitational wave detectors like LIGO and Virgo sense ripples in spacetime caused by cataclysmic cosmic events such as the collision of black holes, opening an entirely new window on the universe beyond electromagnetic radiation. These instruments have revolutionized our understanding of the universe, yet they also reveal how much remains unknown. Each breakthrough seems to open the door to even deeper mysteries. When the Hubble Space Telescope conducted its famous deep field observation in 1995, pointing at an apparently empty patch of sky for 10 consecutive days, it revealed thousands of galaxies never seen before, not just nearby, but stretching back almost to the beginning of time. The James Webb Space Telescope has pushed this frontier even further, revealing galaxies that formed much earlier than our theories predicted possible. These observations challenge our models of galaxy formation and evolution, suggesting there's still much to learn about the universe's early history. Consider the scale of space itself. If our entire solar system, from the Sun to the orbit of Neptune, were reduced to the size of a coin, the Milky Way galaxy would span the North American continent. And if the Milky Way were the size of a coin, the observable universe would be roughly the size of Earth. At each level of this cosmic zoom, we find new structures, new patterns, and new puzzles waiting to be solved. Galaxies cluster together in enormous structures called superclusters, which in turn form even larger filaments and walls, separated by immense voids nearly empty of matter. This cosmic web, spanning billions of light years, represents the largest known structures in the universe, yet we still don't fully understand how they formed. The universe operates according to physical laws that often defy our everyday intuition. At the subatomic scale, quantum mechanics describes particles that can exist in multiple states simultaneously, appear and disappear from the vacuum, and become entangled across vast distances, phenomena Einstein himself called spooky action at a distance. At the largest scales, Einstein's relativity reveals that space and time form a unified fabric that can bend, stretch, and even tear under the influence of mass and energy. Black holes, predicted by Einstein's equations and now directly observed, represent regions where spacetime is so severely curved that nothing, not even light, can escape their gravitational pull. Yet we still lack a unified theory that reconciles quantum mechanics with general relativity, a theory of everything that would describe all fundamental forces and particles. Between these extremes lies the messy, complex universe we inhabit, a universe where stars forge heavy elements in their cores and scatter them throughout space when they die in spectacular supernova explosions, where gravity sculpts clouds of gas and dust into new generations of stars and planets, where, on at least one world, chemistry gave rise to biology and simple organisms evolved into beings capable of contemplating their own origins. Our very bodies are made of star stuff, carbon, oxygen, nitrogen, and other elements created in stellar furnaces billions of years ago. As astronomer Carl Sagan famously observed, we are a way for the cosmos to know itself. But perhaps the most profound aspect of our cosmic ignorance is what some philosophers call the unknown unknowns, the questions we haven't even thought to ask yet, the phenomena we lack the conceptual framework to imagine. Throughout history, scientific revolutions have not just answered existing questions, but revealed entirely new realms of inquiry. Before the invention of the telescope, no one wondered about the composition of distant stars or the nature of galaxies. Before quantum mechanics, no one pondered wave-particle duality or vacuum energy. Before relativity, no one considered whether space and time could bend. What fundamental aspects of reality still lie beyond our conceptual horizons? What revolutions in thought await future generations of astronomers and physicists? Our journey through cosmic history is also a journey through human history, a testament to our enduring curiosity and persistence. From Stonehenge and the pyramids of Giza, aligned with celestial events, to CERN's Large Hadron Collider, probing the fundamental particles of matter, from Galileo's simple telescope to the extremely large telescope currently under construction in Chile, from Newton's mathematical description of gravity to Einstein's revolutionary reconception of space and time, we have dedicated enormous resources to understanding our cosmic context. This quest has yielded not just scientific knowledge, but profound philosophical insights about our place in the universe. The history of astronomy is also a history of humility. Each major discovery has further dislodged humanity from the center of the cosmos. We learned that Earth is not the center of the solar system, that the Sun is not the center of the galaxy, that the Milky Way is not the only galaxy, and that even our local group of galaxies is just one small cluster in an inconceivably vast cosmic web. We've discovered that the chemical elements that make up our bodies were forged in stars that died billions of years ago, and that the very atoms within us are mostly empty space. Yet far from diminishing our significance, these revelations have connected us more deeply to the cosmos. We are not separate from the universe. We are part of its ongoing story. As we stand at the threshold of a new era in space exploration, with plans to return to the Moon, visit Mars, establish permanent human presence beyond Earth, and perhaps one day venture beyond our solar system, we carry with us this dual legacy of discovery and humility. We know more about the universe than any previous generation, yet we remain aware of how much lies beyond our grasp. The cosmos is not just stranger than we imagine, as biologist J.B.S. Haldane suggested, but stranger than we can imagine. Our quest to understand the cosmos has practical applications as well. Technologies developed for space exploration have transformed life on Earth, from satellite communications to weather forecasting, from GPS navigation to medical imaging. The precision required to point a space telescope or land a rover on Mars drives innovations that benefit humanity in countless ways. Moreover, the perspective gained from space exploration, seeing Earth as a pale blue dot, a fragile oasis in the cosmic darkness, has profoundly influenced our awareness of our planet's uniqueness and vulnerability. In this documentary, we will explore the greatest mysteries of the cosmos, the questions that keep astronomers awake at night and drive the next generation of scientific inquiry. We will venture into the darkest corners of the universe, confront paradoxes that challenge our understanding of reality, and imagine futures where today's mysteries might become tomorrow's textbook facts. We'll examine phenomena that stretch the limits of human comprehension, from the infinitesimal quantum realm to the vast cosmic structures spanning billions of light years. Our journey will take us to the edge of the observable universe and to the theoretical limits of physics. We'll consider questions that blend science with philosophy. Does time have a beginning or an end? Is our universe unique or part of a vast multiverse? Could intelligent life exist elsewhere? And if so, why haven't we detected it? What is the ultimate fate of the cosmos? Along the way, we'll meet the scientists and thinkers who are pushing the boundaries of knowledge, operating the world's most powerful telescopes, developing new theoretical frameworks, designing experiments to detect the previously undetectable, and building the next generation of space observatories. Their work combines cutting-edge technology with profound human curiosity, continuing a tradition of cosmic exploration that stretches back to the dawn of civilization. Our cosmic journey begins with something invisible yet incredibly influential, a substance that seems to permeate the universe, affecting the motion of stars and galaxies, yet has never been directly detected. It makes up roughly 27% of the universe's mass-energy content, outweighing ordinary matter more than 5 to 1. This mysterious substance is dark matter, and understanding it may be the key to unlocking many other cosmic enigmas. Dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes. We know it exists only because of its gravitational effects on visible matter, the stars and galaxies we can see. This invisible scaffolding shapes the large-scale structure of the universe, guiding the formation of galaxies and galaxy clusters throughout cosmic history. Yet despite decades of searching, we have yet to identify what dark matter actually is, a humbling reminder of how much remains beyond our understanding. In the vast cosmic theatre, dark matter plays a leading role that we cannot see. Its presence is felt rather than observed, a cosmic phantom that refuses to interact with light, yet exerts a profound gravitational influence across the universe. The story of dark matter begins not with its discovery, but with a puzzle that emerged when astronomers began studying the rotation of galaxies and the movement of celestial bodies on the grandest scales. It is a mystery that continues to challenge our understanding of the fundamental nature of the universe. In the 1930s, Swiss astronomer Fritz Zwicky was examining the Coma cluster, a dense collection of over 1,000 galaxies located about 321 million light-years from Earth in the constellation Coma Berenices. Using the Mount Wilson Observatory's 100-inch telescope, he studied the velocities of galaxies within the cluster and made a startling observation. When he calculated the mass needed to hold this cluster together based on its visible light output, using a measure called the mass-to-light ratio, and compared it to the mass implied by the galaxy's movements according to the virial theorem, he found a striking discrepancy. The cluster appeared to contain about 400 times more mass than could be accounted for by visible matter alone. Without this additional mass, the galaxies would be moving so quickly that the cluster would fly apart, yet it remained gravitationally bound. Zwicky proposed that some form of Dunkel materia, dark matter, must be responsible for providing the extra gravitational pull. Despite the profound implications of his finding, his revolutionary idea remained largely overlooked for decades, dismissed as either an observational error or a minor curiosity. The mystery deepened in the 1970s, when American astronomer Vera Rubin, working alongside instrument maker Kent Ford at the Carnegie Institution of Washington, conducted detailed studies of the rotation of spiral galaxies, most notably the Andromeda Galaxy, also known as Messier 31. They used a spectrograph to measure the Doppler shift in the light from different parts of the galaxy, allowing them to determine how quickly stars were moving at different distances from the galactic center. According to Newtonian physics and common sense, stars at the outer edges of galaxies should orbit more slowly than those near the center, just as planets farther from the sun move more slowly in our solar system. This relationship, known as Keplerian motion, predicts that orbital velocity should decrease with the square root of the distance from the center of mass. Instead, Rubin and Ford found something completely unexpected. Stars throughout a galaxy orbit at roughly the same speed, regardless of their distance from the galactic center. These flat rotation curves directly contradicted the predictions of Newtonian gravitational theory based on visible matter. The data suggested that these cosmic pinwheels contain far more mass than meets the eye, and that this extra mass is distributed differently than the visible stars and gas, extending far beyond the visible boundaries of the galaxy in a roughly spherical distribution. The extra mass couldn't be seen with any telescope, but had to exist to explain the observed motion. Rubin's meticulous observations, initially met with skepticism, were soon confirmed in galaxy after galaxy, providing compelling evidence for Zwicky's overlooked concept of dark matter. To visualize this problem more concretely, imagine our solar system with the same anomaly. Mercury, the innermost planet, orbits the Sun at about 47 kilometers per second, while Neptune, at the outskirts of our planetary system, crawls along at just 5 kilometers per second. If our solar system had a flat rotation curve like galaxies do, Neptune would be racing around the Sun at the same speed as Mercury, a physical impossibility unless there was substantial unseen mass extending far beyond Neptune's orbit, providing the additional gravitational pull to maintain such high orbital velocities at great distances. In galaxies, this extra mass forms a vast spherical halo of dark matter that extends far beyond the visible disk of stars, containing perhaps 10 times the mass of all the visible stars, gas and dust combined. The evidence for dark matter has only grown stronger in the decades since Rubin's pioneering work. When we observe light from distant galaxies, we sometimes see it bend around massive galaxy clusters in between, a phenomenon called gravitational lensing. First predicted by Einstein's theory of general relativity and confirmed during a solar eclipse in 1919, gravitational lensing occurs because mass curves the fabric of space-time, causing light to follow this curved path rather than traveling in a straight line. By carefully measuring these distortions, astronomers can map the distribution of mass in the lensing clusters with remarkable precision. Time and again, these maps reveal substantially more mass than the visible stars and gas can account for, and show that this mass extends well beyond the boundaries of the visible galaxies. In some remarkable cases, like the Sloan Great Wall and other large-scale structures, we can even map the three-dimensional distribution of dark matter across vast regions of space, revealing an invisible cosmic web that underpins the visible universe. Perhaps the most dramatic evidence comes from colliding galaxy clusters. The Bullet Cluster, officially designated 1E0657-5E6, and located about 3.7 billion light-years away in the constellation Carina, provides what many consider the most compelling evidence for dark matter's existence. This system consists of two galaxy clusters that collided at the staggering speed of about 6 million kilometers per hour. As they passed through each other, the visible gas clouds, which make up most of the ordinary matter in clusters, collided, heated to millions of degrees, and slowed down due to electromagnetic interactions. This superheated gas, visible in X-ray images taken by the Chandra X-ray Observatory, appears pink in composite images and clearly shows the shockwave that gives the Bullet Cluster its name. Meanwhile, the galaxies themselves, being more widely separated from each other, sailed through relatively unimpeded, like ghost ships passing in the night. When astronomers mapped the mass distribution using gravitational lensing observations from the Hubble Space Telescope and ground-based observatories, they found that most of the mass had stayed with the galaxies rather than with the gas. In the composite images, this mass appears as blue halos encompassing the galaxy concentrations, but separated from the pink regions of hot gas. This clear separation of mass from visible matter strongly suggests that most of a galaxy cluster's mass consists of dark matter particles that, like the galaxies, pass through the collision without interacting with each other or with the gas. This observation is particularly difficult to explain with modified gravity theories, making the Bullet Cluster what some physicists call a smoking gun for dark matter's existence. Similar separations have been observed in other colliding clusters, such as MAX J0N2 5.4 Hunwu 2, sometimes called the baby bullet, and Abell 520, the train wreck cluster, though the latter shows some puzzling features that don't perfectly align with simple dark matter models. Each of these cosmic collision sites serves as a natural laboratory for testing our understanding of dark matter and its properties. The presence of dark matter also helps explain how galaxies formed in the first place. The cosmic microwave background radiation, the afterglow of the Big Bang discovered in 1965 by Arno Penzias and Robert Wilson, shows that the early universe was remarkably uniform, with density variations of only about 1 part in 100,000. Computer simulations of cosmic evolution show that with such small initial variations, the ordinary matter in the early universe would have remained too diffuse to collapse into the galaxies we see today within the available time. Dark matter, which interacts only through gravity and not through electromagnetic forces, could begin clumping together much earlier, before the universe became transparent to light, about 380,000 years after the Big Bang. These early dark matter concentrations created gravitational wells into which ordinary matter could later fall, seeding the formation of the first stars and galaxies. This process, known as hierarchical structure formation, explains both the overall distribution of galaxies and their internal structure. These simulations, when they include dark matter, produce virtual universes remarkably similar to our own, with the same cosmic web of filaments, clusters, and voids that we observe in the actual cosmos. The Millennium simulation, completed in 2005, and more recent projects like Illustris TNG, demonstrate how dark matter's gravitational influence shapes the large-scale structure of the universe in ways that match our observations. Without dark matter, these simulations fail to produce realistic galaxies and galaxy clusters. So what exactly is this mysterious substance that shapes our universe, yet remains invisible to our instruments? The leading theory is that dark matter consists of as yet undiscovered subatomic particles that interact with ordinary matter primarily through gravity. Unlike the protons, neutrons, and electrons that make up ordinary matter, dark matter particles would not interact via the electromagnetic force. They neither emit nor absorb light, which explains their invisibility. They may interact via the weak nuclear force, but even this interaction would be extremely rare and difficult to detect. This property places dark matter outside the standard model of particle physics, the remarkably successful theory that describes all known particles and their interactions, suggesting that dark matter might offer a window into entirely new physics. Physicists have proposed numerous candidates for these elusive particles, creating a veritable zoo of hypothetical entities. Among the most studied are weakly interacting massive particles, or WIMPs. As their name suggests, these hypothetical particles would interact via the weak nuclear force, one of the 4 fundamental forces alongside gravity, electromagnetism, and the strong nuclear force, and have significant mass, perhaps 10 to 1,000 times the mass of a proton. Mathematical models suggest that if WIMPs exist with certain properties, they would have been produced in the right amounts during the Big Bang to account for the dark matter we infer today. This coincidence, sometimes called the WIMP miracle, made them the leading dark matter candidate for many years. Another candidate is the axion, a hypothetical particle originally proposed in 1977 by physicists Roberto Peccei and Helen Quinn to solve a problem in quantum chromodynamics, the theory of the strong nuclear force. The strong CP problem, as it's known, involves the puzzling absence of certain symmetry violations in strong nuclear interactions. If axions exist, they would naturally explain this absence. These particles, if they exist, would be extremely light, perhaps 1 trillion times lighter than an electron, but could still account for dark matter if they were produced in sufficient quantities in the early universe and later condensed into a Bose-Einstein condensate. a state of matter in which particles behave collectively as a single quantum entity. Other, more exotic possibilities include sterile neutrinos, hypothetical particles related to the known neutrinos but not interacting via the weak force, gravitanos, the supersymmetric partner of the hypothetical graviton, self-interacting dark matter, which could form complex structures analogous to atoms, fuzzy dark matter, composed of extremely light bosons with wave-like properties, and even primordial black holes, formed in the first seconds after the Big Bang rather than from collapsed stars. The quest to detect these particles directly has spawned a global network of increasingly sophisticated experiments, often housed in unusual locations, deep underground, shielded from cosmic rays and other sources of interference by thousands of feet of rock. Detectors wait patiently for the rare interaction between a dark matter particle and ordinary matter. The Large Underground Xenon, LWX experiment, housed in a former gold mine in Lead, South Dakota, used 370 kilograms of liquid xenon as a target medium. Liquid xenon offers several advantages. It's dense, increasing the chances of a collision. It's highly pure, reducing background noise, and it's excellent at scintillation, the process of emitting light when struck by a particle. If a dark matter particle were to collide with a xenon atom, it would produce a tiny flash of light and a few ionized electrons, which sensitive photomultiplier tubes could detect. Similar experiments are running in laboratories around the world, from the Gran Sasso National Laboratory deep within the Gran Sasso Mountain in Italy, home to experiments like Xenon 1T and D, AMA Libra, to the China Jinping Underground Laboratory in Sichuan Province, the deepest underground laboratory in the world at 2,400 meters below the surface. Each uses different target materials and detection techniques, providing complementary approaches to the search. Some, like the Axion Dark Matter Experiment, ADMX, at the University of Washington, are designed specifically to look for axions rather than WIMPs, using strong magnetic fields and resonant cavities to potentially convert axions into detectable photons. So far, none of these experiments has detected a convincing dark matter signal that has been independently confirmed, though there have been tantalizing hints. The DAMA Libra experiment has for years reported an annual modulation in their detector that could be consistent with dark matter interactions, varying as Earth moves with and against the galaxy's rotation throughout the year. However, other experiments with similar or greater sensitivity have failed to confirm this result, leading to ongoing debates about its interpretation. The lack of definitive detection has led to tighter and tighter constraints on the possible properties of dark matter particles, ruling out large regions of parameter space and forcing theorists to refine their models. Meanwhile, particle physicists at the Large Hadron Collider, LHC, near Geneva, Switzerland, are approaching the problem from the opposite direction. By smashing protons together at nearly the speed of light, they hope to create dark matter particles momentarily before they vanish from the detector. Since these particles would leave no direct trace in the detector, physicists look for missing energy and momentum in the collision debris, a telltale sign that something invisible carried away some of the energy and momentum from the collision. Specific search strategies include looking for events where a single particle, such as a photon or a boson, recoils against invisible dark matter particles, creating an imbalance in the detected momentum. So far, these searches too have come up empty, ruling out some of the simplest dark matter models and pushing the theoretical community to explore more complex possibilities. Space-based instruments join the hunt as well, offering different windows on dark matter's possible properties. The Alpha Magnetic Spectrometer, AMS-02, mounted on the International Space Station, searches for antimatter particles that might be produced when dark matter particles annihilate each other. Some theories predict that dark matter and anti-dark matter could meet and destroy each other, producing ordinary particles and antiparticles that AMS might detect. The Fermi Gamma Ray Space Telescope, launched in 2008, scans the sky for gamma rays that could be produced by similar annihilation events in regions of high dark matter density, such as the center of our galaxy or nearby dwarf galaxies. Several analyses of Fermi data have found possible dark matter signals, including a gamma-ray excess from the galactic center, but alternative explanations involving conventional astrophysical sources remain viable, despite decades of searching and billions of dollars invested in increasingly sensitive detectors. Dark matter continues to elude direct detection. This persistent invisibility has led some physicists to question whether dark matter particles exist at all. Perhaps, they suggest, our understanding of gravity itself needs revision at galactic scales and beyond. After all, the evidence for dark matter is entirely gravitational. We infer its existence because objects in the universe move as if subject to more gravity than visible matter can provide. Could our theories of gravity, developed and tested primarily in our solar system, be incomplete when applied to the vastly different scales of galaxies and the cosmos? Modified Newtonian dynamics, or MOND, represents one such alternative approach. Proposed by Israeli physicist Mordechai Milgrom in 1983, MOND suggests that Newton's laws of motion require modification at the extremely low accelerations typical of galactic outskirts. According to MOND, below a certain acceleration threshold, about 1/10,000,000th of the acceleration experienced at Earth's surface, the gravitational force begins to decrease more slowly with distance than in standard Newtonian theory. With this adjustment, galaxies could exhibit flat rotation curves without additional invisible matter, as the stars at the outskirts would experience stronger gravitational attraction than Newtonian physics would predict. Similarly, theories like TVS, tensor vector scalar gravity, proposed by Jacob Bekenstein, and MOGA, modified gravity, developed by John Moffat, attempt to extend or modify Einstein's theory of general relativity to explain cosmic observations without dark matter. These modified gravity theories have had some successes, particularly in explaining the rotation curves of individual galaxies and certain empirical relationships like the Tully-Fisher relation, which connects the brightness of spiral galaxies to their rotation speeds. MOND, in particular, makes specific predictions about how galaxy rotation relates to visible mass, predictions that often match observations with remarkable precision. However, these theories struggle to account for observations on larger scales, such as the behavior of galaxy clusters and the cosmic microwave background, the afterglow of the Big Bang. The bullet cluster, with its clear separation of mass from visible matter, poses a particular challenge for modified gravity theories, which would generally predict that gravitational effects should follow the distribution of visible matter. Most cosmologists still favor the dark matter explanation, though they acknowledge that a conclusive detection of dark matter particles would be necessary to settle the debate definitively. The implications of dark matter extend far beyond astronomy and cosmology. Its existence suggests that the standard model of particle physics, our current best understanding of the fundamental particles and forces in the universe, is incomplete. Developed throughout the latter half of the 20th century and culminating with the discovery of the Higgs boson in 2012, the standard model has been remarkably successful at explaining particle interactions and predicting new particles before their discovery. However, it includes no particle with the properties required for dark matter. The discovery of a dark matter particle would therefore represent a major breakthrough, potentially opening a window into a dark sector of particles and forces that interact only weakly with the familiar matter of our everyday experience. Dark matter also plays a crucial role in our understanding of cosmic history and the ultimate fate of the universe. Its gravitational pull slows the expansion of the universe, counteracting to some degree the mysterious dark energy that accelerates this expansion. The balance between these invisible components will determine whether the universe expands forever or eventually collapses back on itself. Furthermore, dark matter's properties could influence the distribution of galaxies on the largest scales, the formation of the earliest structures in the universe, and even the long-term survival of stars and planets as galaxies evolve. For all its invisibility, dark matter shapes the visible universe in profound ways. It forms the scaffolding upon which galaxies and larger structures are built, It guides the evolution of the cosmos from the nearly uniform state shortly after the Big Bang to the rich complexity we observe today. Without dark matter, we ourselves might not exist. The Milky Way might never have formed, or might have developed so differently that our solar system never coalesced from its interstellar clouds. The stars that forged the heavy elements in our bodies might never have ignited. Dark matter's gravitational influence touches every aspect of cosmic evolution, from the largest structures spanning billions of light years to the conditions that allow for life on at least one small planet. Perhaps the most humbling aspect of dark matter is what it reveals about our cosmic ignorance. For all our technological prowess and scientific progress, we have yet to identify the second most abundant component of the universe, a substance that outweighs ordinary matter 5 to 1. Our most advanced theories and instruments have narrowed the possibilities and ruled out many candidates, but the true nature of dark matter remains elusive. This invisibility serves as a reminder that the universe does not reveal its secrets easily or completely, that our knowledge remains partial and provisional, and that fundamental surprises may await us, even in seemingly well-understood domains of physics. The search continues with ever more sensitive detectors, more powerful particle accelerators, and more precise astronomical observations. The Xenon NT experiment in Italy, an upgrade to the previous xenon detector, uses 8.3 tons of liquid xenon to search for dark matter interactions, while the Luak Zeppelin LZ experiment in South Dakota employs 10 tons, increasing sensitivity by orders of magnitude over previous experiments. The Vera C. Rubin Observatory, currently under construction on Cerro Pachon in Chile, and named for the astronomer who provided crucial evidence for dark matter, will conduct a 10-year survey of the southern sky, creating the most detailed map yet of the distribution of matter in the universe. Dark matter reminds us that the universe does not reveal its secrets easily. It challenges us to develop new technologies, new theories, and new ways of thinking about physics, like the elusive neutrino, which was postulated in 1930 by Wolfgang Pauli to explain missing energy in radioactive decay, but not directly detected until 1956 by Clyde Cowan and Frederick Reines. Dark matter may require decades of persistent effort before yielding its mysteries, or perhaps, like the luminiferous ether that physicists once believed permeated space as a medium for light waves, before Einstein's special relativity rendered it unnecessary, it may lead us to reconceptualize our understanding of fundamental physics in ways we cannot yet imagine. As we grapple with the puzzle of dark matter, we find ourselves in the position of the blind men examining an elephant in the ancient parable. Each experiment, each observation provides a different perspective on this cosmic behemoth, but the complete picture remains beyond our grasp. Yet, this is the essence of science, pushing against the boundaries of the unknown, revising our understanding as new evidence emerges, and remaining open to possibilities that challenge our most cherished assumptions. The mystery of dark matter serves as a humbling reminder that even in the 21st century, with our array of sophisticated instruments and mathematical models, the universe still harbors secrets on the most fundamental level. We look out into the cosmos and find that most of what exists lies beyond our direct perception, a sobering realization, but also an exciting frontier for discovery. The search for dark matter represents one of the great scientific quests of our time, a collaborative effort spanning continents and disciplines, driven by the profound human desire to understand our cosmic context. As significant as dark matter is, comprising over a quarter of the universe's energy mass budget, it pales in comparison to an even more mysterious component, dark energy. This enigmatic force drives the accelerating expansion of the universe, pushing galaxies apart at an ever-increasing rate. While dark matter pulls things together through gravity, dark energy pushes them apart, creating a cosmic tug-of-war whose outcome will determine the ultimate fate of our universe. Dark energy makes up a staggering 68% of the universe's energy mass content, making it the dominant component of the cosmos. Yet we understand even less about its nature than we do about dark matter. To continue our journey through the unknown universe, we must confront this profound cosmic puzzle. If dark matter represents a profound cosmic mystery, dark energy presents an even deeper enigma. While dark matter at least manifests its presence through gravitational effects that we can measure and map, dark energy remains far more elusive. Yet this invisible force appears to be the dominant component of our universe, comprising roughly 68% of its total mass energy content. Dark energy is driving one of the most surprising discoveries in modern cosmology. The universe is not just expanding, but accelerating in its expansion, growing ever faster as cosmic time unfolds. The story of dark energy begins in the late 1990s with two independent teams of astronomers, the Supernova Cosmology Project led by Saul Perlmutter, and the High-Z Supernova Search Team led by Brian Schmidt and Adam Riss. Both groups were using Type Ia supernovae as standard candles to measure vast cosmic distances. These supernovae occur when white dwarf stars in binary systems accumulate matter from their companion stars until they reach a critical mass, about 1.4 times the mass of our Sun, at which point they explode with remarkably consistent brightness. The teams expected to find that the expansion of the universe was slowing down over time due to the gravitational attraction of all the matter within it. Just as a ball thrown upward gradually slows due to Earth's gravity, the universe's expansion should be decelerating due to the mutual gravitational pull of all its contents. The question was simply how much this deceleration was occurring, which would reveal the density of matter in the universe and ultimately its fate. What they found instead was profoundly unexpected. The most distant supernovae, whose light had been traveling toward us for billions of years, were about 25% fainter than they should have been if the universe's expansion was slowing down. The only explanation was that these supernovae were actually farther away than expected, meaning the expansion of the universe had been accelerating during the billions of years their light journeyed to Earth. Something was overwhelming the gravitational attraction of matter and pushing the cosmos apart at an ever-increasing rate. The discovery, announced in 1998, initially met with skepticism. The teams themselves had scrutinized their data for months, looking for any systematic errors or alternative explanations. Could dust in distant galaxies be dimming the supernovae? Were ancient supernovae intrinsically different from modern ones? Might gravitational lensing by intervening matter be affecting the observations? One by one, these possibilities were examined and ruled out. Further observations confirmed the findings, and the mysterious force driving this acceleration was dubbed dark energy. Perlmutter, Schmidt, and Ries were awarded the 2011 Nobel Prize in Physics for this groundbreaking discovery, which fundamentally changed our understanding of the cosmos. As the Nobel Committee stated, they had discovered the most enigmatic phenomenon in all of physics. Subsequent observations have only strengthened the case for dark energy and confirmed that we live in a universe dominated by this mysterious force. Studies of the cosmic microwave background radiation, the afterglow of the Big Bang, have provided crucial independent evidence. Satellites like WMAP and Planck have mapped tiny temperature fluctuations in this radiation with increasing precision. These fluctuations reveal that the universe is geometrically flat and that its total energy density matches what physicists call the critical density. Combined with measurements of ordinary and dark matter, which account for roughly 32% of this critical density, these observations confirm that something like dark energy must make up the remaining 68%. Large-scale galaxy surveys have provided yet another line of evidence. Projects like the Sloan Digital Sky Survey, the Dark Energy Survey, and the Baryon Oscillation Spectroscopic Survey have mapped the three-dimensional distribution of millions of galaxies across billions of light-years. These observations track how the clustering of galaxies has changed throughout cosmic history, providing independent confirmation of dark energy's influence on cosmic expansion. Weak gravitational lensing offers a fourth method for studying dark energy. As light travels from distant galaxies to Earth, its path is slightly distorted by the gravitational effects of matter along the way. By statistically analyzing the shapes of millions of galaxies at different distances, astronomers can map the growth of cosmic structure over time and measure how this growth has been influenced by dark energy's opposing effect. The remarkable consistency of results from these different methods has established dark energy as a cornerstone of the standard cosmological model, often called the Lambda CDM model. According to this model, the universe began with the Big Bang about 13.8 billion years ago, underwent a brief period of extremely rapid expansion called inflation, then continued expanding at a decreasing rate for about 7 billion years as gravity worked to slow this expansion. About 6 to 7 billion years ago, the ever-diluting matter density fell below the constant density of dark energy, allowing acceleration to begin. So what exactly is dark energy? The truth is, we don't know. Unlike dark matter, which cosmologists can at least characterize as some form of massive particle that doesn't interact with light, dark energy remains far more mysterious. Several theoretical possibilities exist, each with profound implications for our understanding of physics and the ultimate fate of the universe. The simplest explanation, and currently the one that best fits observations, is that dark energy is a property of empty space itself, a constant energy density that exists even in a perfect vacuum. This idea traces back to Albert Einstein's cosmological constant, a term he added to his equations of general relativity in 1917. At the time, Einstein believed the universe was static, neither expanding nor contracting, and he introduced this term to counteract the gravitational pull that would otherwise cause the universe to collapse. When Edwin Hubble discovered the expansion of the universe in 1929, Einstein abandoned the cosmological constant, reportedly calling it his greatest blunder. Yet this blunder has made a remarkable comeback. If empty space possesses an intrinsic energy density, a concept supported by quantum field theory, which suggests that even a vacuum contains fluctuating fields and virtual particles that constantly pop in and out of existence, it could produce exactly the kind of repulsive effect needed to explain the accelerating expansion. In quantum field theory, this energy is called vacuum energy or zero-point energy, and it provides a natural candidate for Einstein's cosmological constant. However, this explanation comes with a serious problem known as the cosmological constant problem. When physicists calculate how much vacuum energy should exist based on quantum field theory, they arrive at a value that is approximately 10 to the power of 120 times larger than the value implied by astronomical observations. This discrepancy, often described as the largest disagreement between theory and observation in all of science, has been called the worst theoretical prediction in the history of physics. Either quantum field theory is missing something fundamental, or some unknown mechanism must be suppressing most of this vacuum energy. An alternative explanation suggests that dark energy might not be constant at all, but could change over time, a concept known as quintessence. Named after the fifth element of ancient Greek philosophy, quintessence would be a dynamic field that permeates space, with an energy density that can vary across time. Unlike the cosmological constant, which remains fixed as the universe expands, quintessence could strengthen or weaken over cosmic time. Some quintessence models predict that dark energy might eventually weaken or even reverse, potentially allowing the universe's expansion to slow and eventually collapse in a big crunch. Others suggest it might strengthen, potentially tearing apart galaxies, stars, planets, and even atoms in a scenario called the Big Rip. Most models, however, suggest more modest changes that would still result in eternal expansion, but at varying rates. Current observations slightly favor a constant dark energy density over changing models, but the evidence is not yet conclusive. A third category of explanations suggests that dark energy might not be a real energy at all, but rather an illusion caused by our incomplete understanding of gravity. Just as dark matter could potentially be explained by modifying gravity, rather than postulating new particles. Dark energy might represent a breakdown of Einstein's general relativity at the largest scales. Theories like modified gravity, FR gravity, or massive gravity attempt to alter Einstein's equations to account for the accelerating expansion without introducing new energy components. Testing these alternatives is challenging. Most proposed modifications to general relativity that could explain the accelerating expansion have been ruled out by observations, particularly by gravitational wave detections that confirm Einstein's predictions with remarkable precision. Still, more subtle modifications remain possible, and the search continues for theories that could explain both dark energy and remain consistent with all other observations. Perhaps the most radical explanation comes from string theory and the concept of the multiverse. According to some versions of string theory, our universe might be just one of a vast ensemble of universes, each with different physical laws and constants. In this scenario, the apparent fine-tuning of the cosmological constant, the fact that it has exactly the tiny value needed to allow galaxy formation and eventually life, could be explained by a form of cosmic natural selection. If most universes have much larger vacuum energies that prevent structures from forming, then intelligent observers would naturally find themselves in one of the rare universes with a small enough value to allow their existence. The discovery of dark energy has profound implications for the ultimate fate of our universe. Before this discovery, cosmologists envisioned three possible scenarios for the cosmos: eternal expansion at an ever-decreasing rate, eventual recollapse into a big crunch, or a delicate balance between these extremes. Dark energy has added new possibilities, including eternal acceleration and the more extreme Big Rip scenario in which even fundamental particles are eventually torn apart. Current evidence strongly favors eternal expansion with continued acceleration, meaning that galaxies beyond our local group will eventually disappear from our observable universe as they recede faster than light. In roughly 100 billion years, future astronomers in the Milky Way, by then merged with the Andromeda Galaxy, would see nothing beyond their single island of stars, all other galaxies having receded beyond the cosmic horizon. The evidence of the broader cosmos, and perhaps even the clues that led to the discovery of dark energy, will have faded from view. Understanding dark energy is not merely an abstract scientific pursuit, but a quest to comprehend the ultimate destiny of everything in existence. It touches on fundamental questions about the nature of space, time, energy, and even the possibility of other universes. The acceleration of cosmic expansion represents one of the greatest surprises in the history of cosmology, a reminder that the universe often defies our intuitions and expectations. The practical challenges of studying dark energy are immense. Unlike dark matter, which concentrates in and around galaxies, dark energy appears to be spread uniformly throughout space. This makes it incredibly difficult to study in a laboratory setting. There's no hope of capturing dark energy or isolating it from other effects. Instead, astronomers must rely on vast surveys of the cosmos, tracking how structures evolve over billions of years to tease out dark energy's subtle influence. Several major projects are underway or planned to better constrain the properties of dark energy. The Dark Energy Spectroscopic Instrument will create the largest three-dimensional map of the universe, measuring the light from 35 million galaxies and quasars. The Vera C. Rubin Observatory will conduct the legacy survey of space and time, repeatedly imaging the entire available sky every few nights for 10 years. In space, the European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope will observe billions of galaxies, providing complementary constraints on dark energy models. The connection between dark energy and particle physics runs deep. The discovery of the Higgs boson in 2012 confirmed the existence of the Higgs field, which permeates space and gives elementary particles their mass. The energy density of this field contributes to the vacuum energy, though exactly how much remains uncertain. Some theoretical models suggest that dark energy might be related to another field similar to the Higgs, or to previously unknown particles with unusual properties. One of the most perplexing aspects of dark energy is what physicists call the coincidence problem. Why is the density of dark energy roughly comparable to the density of matter today? In the early universe, matter dominated by many orders of magnitude. In the far future, dark energy will completely dominate as matter continues to dilute through expansion. We happen to live in the relatively brief cosmic epoch, where the two components are within factors of a few of each other. Is this just a coincidence, or does it hint at some deeper connection between dark energy and matter? Beyond its implications for the future of the universe, dark energy touches on profound philosophical questions about the nature of physical law and the limits of scientific explanation. If the anthropic explanation proves correct, that the value of dark energy is what it is, because otherwise we wouldn't be here to measure it, it would represent a shift in how physicists think about explaining fundamental constants. Rather than seeking a unique theory that predicts all constants from first principles, we might need to accept that some aspects of our universe are the way they are by cosmic happenstance. The dark energy puzzle exemplifies both the progress and limitations of modern cosmology. On one hand, we can now measure the expansion history of the universe with remarkable precision, tracking how the relationship between distance and redshift has evolved over billions of years. On the other hand, we remain profoundly uncertain about what dark energy actually is, with explanations ranging from a simple property of empty space to exotic fields or modifications of Einstein's gravity. This tension between empirical success and theoretical uncertainty is characteristic of paradigm shifts in science. Just as the precise measurements of planetary orbits eventually led to the overthrow of Newtonian gravity in favor of Einstein's general relativity, today's precise measurements of cosmic expansion might be pointing toward a new conception of space, time, and energy that we have yet to fully formulate. The history of science suggests that periods of puzzlement often precede revolutionary insights. For now, dark energy remains the dominant mystery in modern cosmology, a ubiquitous component of our universe that shapes its large-scale evolution, yet resists our attempts at deeper understanding. It reminds us that despite all our technological and intellectual achievements, the universe still harbors secrets at the most fundamental level. The quest to understand dark energy drives the development of ever more powerful telescopes, more sophisticated computer simulations, and more creative theoretical approaches. Perhaps the most remarkable aspect of the dark energy story is how recently it unfolded. Just 3 decades ago, most cosmologists believed the universe's expansion was slowing down, with the only question being, by how much? The discovery of acceleration represents one of the most dramatic reversals in scientific understanding in recent history. It reminds us that even in a field as mature as cosmology, paradigm-shifting discoveries remain possible. As we continue to map and measure the universe with increasing precision, we approach dark energy from multiple angles, constraining its properties and testing alternative explanations. Each new survey and experiment narrows the range of possibilities, gradually illuminating this cosmic shadow. Whether dark energy proves to be a constant property of space, a dynamic field that changes over time, or a sign that our theory of gravity needs revision, its study will continue to drive cosmology forward into new territory. The dark energy puzzle connects to the ultimate fate of our universe and everything in it. Will the cosmos expand forever, growing ever colder and more diffuse as stars burn out and galaxies recede beyond each other's horizons? Will the acceleration eventually become so extreme that it tears apart the fabric of space itself? Or might dark energy weaken over time, potentially allowing gravity to reassert dominance in the far future? The answer lies in understanding this invisible force that currently dominates our universe. As we contemplate dark energy's influence on the cosmic future, we naturally turn to another fundamental question about the universe's development. What determines its ultimate fate? Will the universe expand forever, eventually reaching a state of maximum entropy when no further change is possible? Or might some process reverse this seemingly inevitable march toward heat death? The answers depend not just on dark energy, but on the complex interplay of all cosmic components across timescales far beyond human experience. To understand the universe's destiny, we must explore the possible endpoints of cosmic evolution and the physics that drives them. Throughout human history, cultures around the world have contemplated how the universe might end. Ancient Norse mythology described Ragnarok, a series of cataclysmic events culminating in the submersion of the world beneath water. Hindu cosmology envisions cycles of creation and destruction spanning billions of years. The Book of Revelation in the Christian tradition depicts apocalyptic events leading to a new heaven and earth. These narratives reflect our deep-seated curiosity about cosmic finality. Today, cosmologists approach this question not through mythology, but through the lens of physics and astronomy, using observations of the distant universe and the laws of nature to forecast possible cosmic endings. Unlike our ancestors, we now know that Earth is not the center of creation, but a tiny planet orbiting an ordinary star in a vast cosmos. The fate of our world is intimately tied to the evolution of the universe itself, which began approximately 13.8 billion years ago in the hot, dense state known as the Big Bang. Since then, the universe has been expanding, cooling, and evolving, forming galaxies, stars, and planets along the way. But what lies ahead? Will the universe continue expanding forever, gradually cooling to a state of maximum entropy? Will it eventually collapse back upon itself in a big crunch? Or might something even more exotic await? The quest to determine our cosmic destiny centers on understanding the fundamental forces that drive universal evolution. Gravity, the attractive force between masses described by Einstein's general relativity, works to slow the expansion of the universe. Dark energy, the mysterious repulsive force discovered in the late 1990s, accelerates this expansion. The competition between these opposing influences, along with the properties of matter and energy in all its forms, will shape the universe's future. The simplest scenario, supported by current observations, is known as the Big Freeze, or heat death. In this model, dark energy continues to drive accelerating expansion indefinitely. As the universe grows ever larger, matter and energy become increasingly diluted. Stars burn through their nuclear fuel and fade away. Galaxies beyond our local group recede beyond our cosmic horizon, their light unable to reach us even after an infinite time. Eventually, the observable universe contains only the remnants of the Milky Way and its nearest neighbors, themselves going dark as their stars die. This cosmic heat death unfolds over truly staggering timescales. In about 5 billion years, our Sun will exhaust the hydrogen in its core, swell into a red giant, and eventually shed its outer layers, leaving behind a cooling white dwarf. Similar fates await most stars, with the most massive ones exploding as supernovae or collapsing into black holes. Within 100 trillion years, star formation across the universe largely ceases as the available gas becomes too diffuse to collapse into new stars. The cosmos enters what astronomers call the degenerate era, populated by white dwarfs, neutron stars, and black holes. Even these remnants aren't eternal. Over unimaginably long timescales, 10 to the power of 40 years, protons may decay into lighter particles, gradually eroding the remaining matter. Black holes slowly evaporate through Hawking radiation, with the largest supermassive black holes taking up to 10 to the power of 100 years to disappear completely. Eventually, the universe approaches a state of maximum entropy, a nearly empty void of extremely low energy radiation and fundamental particles, separated by vast distances, continuing to expand and cool forever. This is the ultimate heat death, a universe where no further organized structures can exist and no meaningful work can be performed. An alternative scenario, once considered likely but now disfavored by observations, is the Big Crunch. If the universe contains enough matter and energy to overcome the current expansion, gravity could eventually halt and reverse the cosmic spread. Galaxies would begin moving toward each other rather than away. Space itself would contract, bringing everything closer together. In the final stages, temperatures would rise dramatically as matter compresses, stars would be torn apart, and ultimately all matter would collapse into an infinitely dense, hot singularity similar to the Big Bang, but in reverse. The Big Crunch scenario depends critically on the average density of the universe exceeding a threshold value called the critical density. Current measurements of the cosmic microwave background radiation and large-scale structure suggest that we live in a flat universe with a density very close to critical. However, the discovery of dark energy tips the scales decidedly away from recollapse. Unless dark energy somehow weakens or reverses sign in the distant future, a possibility not ruled out by some theoretical models of quintessence, the universe appears destined for eternal expansion rather than collapse. Intriguingly, some theoretical physicists have proposed that a big crunch need not be the ultimate end, but could potentially lead to a big bounce, a new expansion phase following the collapse. In these cyclic universe models, the cosmos undergoes endless cycles of expansion and contraction, with each bounce potentially creating conditions similar to the Big Bang we observe evidence for. While mathematically elegant, these models face significant challenges, particularly in explaining how entropy, disorder, could be reset with each cycle to allow new complex structures to form. A third scenario, more exotic than either eternal expansion or eventual collapse, is called the Big Rip. This possibility emerges from certain models of dark energy, where its repulsive effect grows stronger over time. If dark energy's strength increases without bound, it could eventually overcome not just the gravitational attraction between galaxies, but also the forces holding individual galaxies, stars, planets, and ultimately atoms together. The fabric of space would be torn apart at all scales in a final catastrophic shredding of reality itself. The Big Rip scenario depends on dark energy having an equation of state parameter, commonly denoted W, with a value less than 1. Current observations constrain W to be very close to 1, consistent with dark energy being a cosmological constant with unchanging strength. However, the measurement uncertainties don't completely rule out values slightly below Pacha 1, leaving open the possibility of a big rip in the extremely distant future, perhaps 100 billion years from now or more. Yet another possibility, still highly speculative, stems from the unstable nature of our current vacuum state. Quantum field theory suggests that what we perceive as empty space may actually be in a metastable state, a false vacuum that could tunnel to a lower energy true vacuum. If a bubble of true vacuum were to form somewhere in the cosmos, it would expand at nearly the speed of light, converting our familiar physics to a completely different set of physical laws in the process. From our perspective, this vacuum decay would be instantaneous and complete, with no warning and no possibility of escape. This scenario, sometimes called the Big Slurp, resembles in some ways the Ice Nine catastrophe in Kurt Vonnegut's novel, Cat's Cradle, where a single seed crystal triggers the freezing of all water on Earth. The likelihood of vacuum decay depends on details of the Higgs field and other aspects of particle physics that remain imperfectly understood. Calculations suggest that if it can happen, it probably would have happened already in the 13.8 billion year history of our universe. The fact that we're still here might indicate that our vacuum is stable after all, or at least extraordinarily long-lived. Nevertheless, this scenario represents another possible end to the universe as we know it, fundamentally different from the gradual cooling of the Big Freeze or the fiery compression of the Big Crunch. Beyond these main scenarios lie even more speculative possibilities involving concepts from string theory, quantum gravity, and other cutting-edge physics. Some theorists propose that our three-dimensional universe might be a brane floating in a higher dimensional space, and that collisions with other branes might periodically reset cosmic conditions. Others suggest that the quantum nature of space and time at the smallest scales might lead to unexpected behaviors at the largest scales or over the longest time periods. The common thread in all these scenarios is the role of entropy, the measure of disorder or randomness in a system. The second law of thermodynamics states that entropy in an isolated system never decreases over time. The universe as a whole appears to be an isolated system, leading inevitably to increasing disorder. The Big Freeze represents the ultimate triumph of entropy, a state of maximum disorder where energy is evenly distributed and no further structured processes can occur. The Big Crunch potentially offers a reset of entropy through mechanisms not yet understood, while the Big Rip and vacuum decay represent alternative paths to cosmic finality with their own entropy implications. The concept of heat death was first proposed in the 1850s by William Thomson, Lord Kelvin, and was based on the thermodynamic principles being developed at that time. Kelvin realized that as energy disperses, the ability to do useful work diminishes. Applied to the cosmos, this principle suggests that the universe will eventually reach a state of thermal equilibrium, where no energy gradients exist to drive physical processes. Modern cosmology has refined these 19th century insights, incorporating Einstein's relativity, quantum mechanics, and observational discoveries about dark energy and dark matter. The role of black holes in the universe's fate deserves special attention. These incredibly dense objects, formed from collapsed stars or directly from concentrated matter in the early universe, represent the ultimate gravitational sink. Matter and energy that fall into a black hole are, in a sense, removed from the broader cosmic evolution. However, Stephen Hawking's groundbreaking work in the 1970s showed that black holes aren't completely black. They emit radiation through quantum effects near their event horizons, gradually losing mass in the process. Given enough time, far longer than the current age of the universe, even the largest black holes will evaporate completely, returning their energy to the cosmos in the form of extremely dilute radiation. This evaporation process dramatically extends the timeline of cosmic evolution. In the far, far future, perhaps 10 to the power of 100 years from now, even the supermassive black holes at the centers of galaxies will have disappeared, leaving a cosmos populated only by photons, neutrinos, and other fundamental particles, all at nearly the same temperature, just slightly above absolute zero. This ultimate heat death represents a kind of cosmic equilibrium, symmetric, uniform, and incapable of supporting complex structures or life. But might there be escape routes from cosmic doom? Theoretical physicist Freeman Dyson and others have explored whether intelligent life could adapt to the ever-cooling universe by slowing its metabolism and information processing to use energy more efficiently. In principle, a civilization might survive indefinitely in a universe of ever-decreasing temperature by thinking ever more slowly, maintaining a constant number of thoughts with decreasing energy per thought. However, this strategy fails in a universe dominated by dark energy, where matter becomes too diffuse to support even the most efficient computation. The possibility of escaping to other universes offers another speculative avenue. Various multiverse theories suggest that our universe might be one of many, perhaps even infinitely many, existing in a broader cosmic landscape. If travel between universes were somehow possible, through wormholes, quantum tunneling, or mechanisms we haven't yet imagined, intelligent life might migrate to younger, more hospitable regions of the multiverse as our own universe ages toward heat death. Of course, this presupposes that the laws of physics permit such travel, which remains highly uncertain. A more radical possibility involves the spontaneous formation of a new universe from the quantum vacuum. Inflationary cosmology, which describes an extremely rapid expansion in the earliest moments after the Big Bang, suggests that quantum fluctuations can be amplified to cosmic scales under the right conditions. If our universe underwent inflation, might a similar process occur again in the distant future? Could an intelligent civilization even engineer such a process, seeding a baby universe with carefully chosen physical parameters? Such cosmic engineering remains firmly in the realm of science fiction for now, but it represents the ultimate expression of the human drive to transcend limitations. For most practical purposes, the fate of humanity and Earth-based life, will be determined long before any of these cosmic endings come to pass. Our sun will exhaust its core hydrogen and swell into a red giant in about 5 billion years, potentially engulfing Earth's orbit. Even before that, in roughly 1 to 2 billion years, the sun's gradually increasing luminosity will disrupt Earth's climate, likely rendering our planet uninhabitable for complex life. Any long-term future for humanity would require migration to other star systems, a possibility that currently exists only in theoretical discussions and science fiction. The timescales involved in cosmic eschatology are difficult to comprehend. To put them in perspective, if the entire 13.8 billion year history of the universe since the Big Bang were compressed into a single year, with the Big Bang occurring on January 1st and the present moment at midnight on December 31st, then modern humans would have appeared only in the last 20 minutes of December 31st. Yet the timeline of cosmic evolution stretches billions, trillions, or even Google's 10 to the power of 100 of years into the future. The heat death might not occur until a date that, in our calendar analogy, would be millions or billions of years after our compressed cosmic year. These vast timescales raise profound philosophical questions. If the universe is destined for heat death, does that imply that all human achievements, our art, science, technology, and culture, are ultimately meaningless? Or does meaning exist precisely in the brief, luminous interval when conscious beings can appreciate the cosmos, even knowing that both they and it are temporary? Different philosophical traditions offer varying perspectives on these questions, from existentialist emphasis on creating subjective meaning in an indifferent universe to religious frameworks that place cosmic evolution within a broader metaphysical context. Scientific understanding of cosmic fate continues to evolve as observations improve and theories develop. The discovery of dark energy in the late 1990s dramatically shifted expectations from a universe likely to recollapse to one almost certainly expanding forever. Future discoveries, perhaps detecting changes in dark energy's strength over time, or finding evidence for modified theories of gravity, or uncovering quantum effects relevant at cosmic scales, could similarly transform our understanding of ultimate cosmic destiny. Current research relevant to the universe's fate includes precise measurements of the cosmic expansion rate, studies of the cosmic microwave background radiation, large-scale galaxy surveys, and theoretical work in particle physics and quantum gravity. The Dark Energy Survey, the James Webb Space Telescope, the European Space Agency's Euclid mission, and other projects aim to constrain dark energy's properties with unprecedented precision. Meanwhile, particle accelerators like the Large Hadron Collider probe the fundamental forces and particles that dictate cosmic evolution. The various cosmic doomsday scenarios differ dramatically in their timelines and characteristics. The Big Freeze unfolds gradually over trillions upon trillions of years, with stars slowly dying, galaxies growing isolated, and entropy inexorably increasing. The Big Crunch, if it could occur, would become noticeable only after many billions of years as the cosmic expansion slowed and reversed. The Big Rip would begin with the dispersion of galaxy clusters, proceed to the disruption of individual galaxies and solar systems, and end with the literal tearing apart of atoms. Vacuum decay would propagate at nearly the speed of light and transform our region of space essentially instantaneously from our perspective. Information conservation poses conceptual challenges for any cosmic endpoint. Quantum mechanics suggests that information cannot be truly destroyed, yet the heat death scenario appears to erase all meaningful structure from the universe. This tension, related to the famous black hole information paradox, remains an active area of theoretical investigation. Some proposed resolutions involve subtle quantum correlations persisting even in an apparently featureless thermal equilibrium, potentially preserving information in principle, though not in any practically retrievable form. The role of entropy in cosmic evolution connects the universe's beginning to its end. The Big Bang appears to have been a state of extraordinarily low entropy, which seems puzzling given that we might expect the universe to have begun in a high entropy state of thermal equilibrium. This past hypothesis problem has led some theorists to propose that the Big Bang was not actually the beginning, but rather a special phase in an eternal cosmos with peculiar entropy properties. Understanding the universe's fate may require resolving this entropy puzzle, potentially revealing deep connections between initial and final cosmic states. Quantum fluctuations offer another perspective on cosmic finality. According to quantum field theory, even in the near-perfect vacuum of a heat-death universe, random fluctuations would occasionally occur. Given infinite time, these fluctuations could, in principle, produce arbitrarily improbable events, including, perhaps, the spontaneous formation of organized structures, or even new, Big Bang-like events. This Boltzmann brain paradox asks whether it's more likely that we exist as regular observers in an evolving universe, or as random fluctuations in an equilibrium state. For now, the evidence points most strongly toward a big freeze scenario, with the universe expanding forever, gradually cooling, and eventually reaching a state of maximum entropy. But the frontiers of theoretical physics and observational cosmology continue to advance, potentially revealing new possibilities or refining our understanding of known ones. The quest to determine the universe's ultimate fate represents one of the most profound scientific endeavors, connecting fundamental physics to the deepest philosophical questions about existence, time, and meaning. As we consider these cosmic timescales and possibilities, we find ourselves in a unique position, conscious beings capable of comprehending both our origins in the Big Bang and our potential cosmic futures. Whatever the ultimate fate of the universe may be, our ability to contemplate it represents something remarkable. The universe has evolved to a state where a small portion of it can reflect on its own existence, history, and destiny. In that reflection lies something profound, regardless of whether the cosmos ends in ice, fire, or something stranger still. The current chapter of cosmic history, the era of stars, galaxies, and life, represents a brief but remarkable period when energy gradients allow complex structures to form and persist. Rather than lamenting the universe's eventual descent into disorder, perhaps we might celebrate the extraordinary confluence of conditions that permit our existence in this particular cosmic moment. The universe's fate may be sealed, but its present offers wonders worthy of our attention. From the smallest quantum fluctuations to the largest galactic superclusters. As we turn our gaze from the far future back to present concerns, we might consider what came before the universe we observe, the question of cosmic origins that complements our exploration of cosmic endings. If the universe will ultimately end, how did it begin? Was the Big Bang truly the beginning of time, or was it merely a transition in a larger cosmic history? To understand our universe's fate fully, we must also understand its birth and earliest moments, when the conditions were set that would determine its entire evolution. And so we turn from the cosmic future to the cosmic past, from endings to beginnings. As we gaze into the vastness of space, peering through our most powerful telescopes, we catch glimpses of the universe's infancy, light that has traveled for nearly 14 billion years to reach us. But what came before? What preceded the violent birth of space, time, and matter that we call the Big Bang? This question drives some of the most profound research in modern cosmology, pushing us to the very limits of physics and human understanding. The Big Bang theory stands as one of science's greatest achievements, a comprehensive explanation for how our universe evolved from a hot, dense state to the vast cosmos we observe today. Yet despite its extraordinary success, the theory has limits. It cannot tell us what ignited this cosmic explosion, nor can it describe the universe in its first fraction of a second. As we approach time zero, our equations break down, leaving us at the threshold of a cosmic unknown. For decades, scientists believed the universe began with a singularity, an infinitely hot, dense point where the laws of physics simply fail. At this singularity, space and time as we understand them cease to exist. The temperature would have been unimaginably high, perhaps reaching 10 to the 32 degrees Kelvin, a number so vast it defies comprehension. At such temperatures, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, would have been unified into a single superforce. But what could create such extreme conditions in the first place? The singularity concept itself comes from applying Einstein's general relativity to the early universe. When we run the cosmic expansion backward in time, everything converges to a point of infinite density. But physicists recognize this as a sign that our theories are incomplete, not necessarily that the universe actually emerged from a mathematical infinity. As Stephen Hawking once remarked, asking what's north of the North Pole is meaningless. Perhaps the question of what came before the beginning of time is similarly misconceived. Cosmic inflation represents our best understanding of these earliest moments. Proposed by physicist Alan Guth in 1979, inflation theory suggests that the universe underwent a period of exponential expansion in the first trillionth of a trillionth of a trillionth of a second after its birth. In this fleeting instant, the cosmos expanded faster than the speed of light, growing from smaller than a subatomic particle to the size of a grapefruit. To put this growth in perspective, if inflation had lasted just a little longer, 1 second instead of a fraction of a nanosecond, our observable universe would be vastly larger than it is now, perhaps billions of times larger than what we can currently detect with our most powerful instruments. What drove this extraordinary expansion? The answer lies in the peculiar properties of space itself. According to inflation theory, the early universe was dominated by an unstable energy field, what physicists call a false vacuum. This false vacuum contained enormous energy density, creating a kind of anti-gravity effect that pushed space apart faster than anything we've observed since. Imagine a ball perched at the top of a hill. It's temporarily stable but poised to roll down. Similarly, the false vacuum was a temporary state that eventually rolled down to a lower energy configuration, releasing its stored energy and ending the inflationary epoch. The evidence for inflation is compelling. It explains why the universe appears so uniform in all directions, why space seems geometrically flat, and how the first seeds of cosmic structure, the tiny fluctuations that would eventually grow into galaxies and galaxy clusters, were sown. The Planck Space Telescope, which mapped the cosmic microwave background radiation with unprecedented precision between 2009 and 2013, revealed patterns that align beautifully with inflation's predictions. The tiny temperature variations in this ancient light, just 1 part in 100,000, match what inflation would produce through quantum fluctuations stretched to cosmic scales. But this raises a deeper question. What created the conditions for inflation to begin? Here we encounter even more speculative terrain, where cutting-edge theories attempt to push beyond the inflation boundary. Some theories suggest that inflation is eternal, that once it begins, it continues forever in some regions of space while ending in others. In this scenario, our universe is just one bubble in an eternally inflating multiverse, with new bubble universes constantly forming as inflating space produces more and more regions where inflation ends. Other physicists propose that our universe emerged from a quantum fluctuation in a pre-existing state. In quantum mechanics, particles can appear and disappear spontaneously from the vacuum due to energy fluctuations permitted by the uncertainty principle. Virtual particle pairs pop into existence briefly before annihilating each other. Perhaps our entire universe began as a similar fluctuation, a bubble of space-time that emerged from a larger cosmic medium. This notion is closely tied to the idea that the total energy of the universe might be exactly zero, with the positive energy of matter perfectly balanced by the negative energy of gravity. If true, the universe could indeed come from nothing in an energetic sense. This connects to one of the most revolutionary ideas in contemporary cosmology, that time itself may not be fundamental. At the quantum scale, time may behave very differently than our everyday experience suggests. Physicist Carlo Rovelli has proposed that time emerges from quantum entanglements between particles, rather than flowing independently as a fundamental dimension. In quantum gravity, theories like loop quantum gravity, space and time are not continuous but made of discrete units, quanta of space-time, that only appear continuous at larger scales, much as water appears continuous despite being made of distinct molecules. If time is indeed emergent rather than fundamental, asking what happened before the Big Bang might be as meaningless as asking what's north of the North Pole. There would be no before in any conventional sense. Instead, the Big Bang represents a boundary of time itself, a point beyond which the concept of temporal sequence loses meaning. This doesn't mean nothing existed. Rather, it suggests a different mode of existence, not capturable in our time-bound language. The quest to understand pre-Big Bang physics has led to some extraordinarily creative theories. One approach comes from the mathematics of higher dimensions. String theory, which attempts to unify quantum mechanics and general relativity, requires extra spatial dimensions beyond the three we experience. These dimensions might be compactified, curled up so tightly that they're invisible to us, yet crucial for the fundamental physics of reality. String theory offers another perspective on the pre-Big Bang universe. According to this framework, our universe might have originated from the collision of higher dimensional objects called branes, short for membranes. These cosmic sheets exist in dimensions beyond our familiar three spatial dimensions. When two branes collide in the higher dimensional space, the enormous energy released could manifest as a Big Bang in our observable universe. This ekpyrotic scenario, proposed by physicists Paul Steinhardt, Neil Turok, and others, suggests our universe arose not from inflation, but from this cosmic collision. In the ekpyrotic model, two parallel branes in a higher dimensional space approach each other, drawn together by subtle forces. As they near, quantum fluctuations create ripples on their surfaces. When the branes collide, these ripples translate into density variations in the newly formed universe, precisely the sort of variations we observe in the cosmic microwave background. After the collision, the branes separate again, potentially setting up another collision billions of years later. This leads naturally to the concept of a cyclic universe. The cyclic universe model takes this brane perspective further. It suggests our universe undergoes endless cycles of expansion and contraction, with each Big Bang followed by a big crunch billions of years later, which then triggers the next Big Bang. In this view, our universe is just one iteration in an eternal cosmic cycle, with no absolute beginning or end. Each cycle might last trillions of years, first expanding, then gradually slowing, then contracting back to a bounce that initiates the next cycle. This cyclic viewpoint resonates with ancient cosmologies from various cultures. Hindu cosmology describes cycles of creation and destruction lasting billions of years. Ancient Greek philosophers like Heraclitus envisioned a cosmos repeatedly consumed by fire and reborn. Modern cyclic models give these intuitions mathematical precision, suggesting how each cycle might transmit certain properties to the next, while washing away others. There are tantalizing hints that such a cyclic model might be correct. The discovery of gravitational waves by the LIGO experiment in 2015 has opened a new window on the early universe, potentially allowing us to detect echoes from before the Big Bang. If we could observe these primordial gravitational waves with enough precision, they might carry imprints from a previous cosmic cycle. The particular pattern of these waves could distinguish between inflation models and cyclic models, potentially resolving decades of theoretical debate. Quantum loop gravity, another contender for a theory of quantum gravity, suggests a big bounce rather than a big bang. In this scenario, a previous contracting universe reached a minimum size before rebounding into our expanding one. The mathematics of loop quantum cosmology indicates that quantum effects prevent space from shrinking to an infinitely small point, allowing it to transition smoothly from contraction to expansion. This quantum bounce would occur at densities far greater than nuclear density, but still finite. Perhaps when the entire observable universe was compressed to the size of a tennis ball. The Big Bounce scenario solves several problems with the standard Big Bang model. It eliminates the singularity problem, replacing the mathematically troublesome infinity with a quantum transition. It potentially explains why entropy was low at the Big Bang, since the contracting phase before the bounce might have ironed out in homogeneities, like a cosmic pressing machine. And it addresses the question of what came before, another universe, similar to ours but not identical, contracting toward its finale. Even more radical is the idea that our universe emerged through a process called vacuum decay in a parent universe. Just as radioactive atoms can decay into more stable configurations, releasing energy in the process, a metastable vacuum state in a parent universe could tunnel into a lower energy state, creating a bubble that expands at nearly the speed of light. Inside this bubble, space-time and the laws of physics might be entirely different from those outside, potentially explaining why our universe seems so finely tuned for complexity and life. This concept, sometimes called cosmological natural selection, suggests an evolutionary mechanism for universes themselves. Physicist Lee Smolin proposed that black holes might spawn new universes, with each offspring universe having slightly different physical constants than its parent. Over cosmic generations, universes that produce many black holes would have more offspring, leading to a multiverse dominated by universes optimized for black hole production. Interestingly, the conditions that favor black hole formation also seem to favor the emergence of complex chemistry and potentially life, perhaps explaining why our universe seems so hospitable to our existence. The notion that time had a beginning becomes particularly puzzling when we consider the law of conservation of energy, one of physics' most fundamental principles. If energy cannot be created or destroyed, where did all the energy in our universe come from? One answer comes from the remarkable fact that the total energy of the universe might actually be zero. The positive energy of matter and radiation is perfectly balanced by the negative energy of gravitational attraction. In this view, the universe is the ultimate free lunch, a magnificent cosmic structure that required no net energy to create. Physicist Alexander Vilenkin has proposed another perspective, that the universe could have literally tunneled into existence from nothing through a quantum process. In quantum mechanics, particles can tunnel through energy barriers that would be insurmountable in classical physics. Similarly, Vilenkin suggests the universe itself might have quantum tunneled from a state of nothing into existence. This nothing isn't absolute non-existence, but rather a state with no classical space or time, a quantum void from which our universe emerged. The no-boundary proposal developed by Stephen Hawking and James Hartle offers yet another approach. It suggests that asking about the beginning of the universe is like asking about the edge of Earth. Just as the Earth's surface is finite but has no boundary or edge, the universe might be finite in time without having a beginning point. Using the mathematics of quantum gravity, Hawking and Hartle showed how the early universe could be described by a sum over histories approach, where time itself emerges smoothly from a timeless state without any sharp beginning. These theoretical explorations reveal a profound truth. The Big Bang was likely not the beginning of everything, but rather a transformative event in a larger cosmic narrative. The question, what happened before the Big Bang, is gradually shifting from philosophy to physics as our mathematical models and observational techniques improve. Yet we must acknowledge the challenges in testing these pre-Big Bang theories. Most make predictions about phenomena at energy scales far beyond what our most powerful particle accelerators can reach. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, operates at energies around 13 trillion electron volts. But the energies relevant to inflation and pre-Big Bang physics might be a quadrillion times higher. At the so-called grand unified theory scale, or even the Planck scale, where quantum gravity effects become dominant. Similarly, observations of the very early universe are limited by the cosmic microwave background radiation, a boundary we call the surface of last scattering, beyond which the universe was opaque to electromagnetic radiation. This radiation was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this time, photons couldn't travel far without scattering off free electrons, creating a cosmic fog that obscures our view of earlier epochs. However, creative scientists are devising new ways to probe this cosmic dawn. Advanced gravitational wave detectors might detect primordial gravitational waves, ripples in space-time created in the first instance after the Big Bang. These waves, unlike light, can travel through the opaque early universe, potentially carrying information from before the cosmic microwave background. The proposed space-based gravitational wave observatory, LISA, Laser Interferometer Space Antenna, scheduled for launch in the 2030s, might be sensitive enough to detect these primordial ripples. Another approach investigates cosmic magnetic fields. If large-scale magnetic fields were generated before the Big Bang, they might leave distinctive patterns in the polarization of the cosmic microwave background. The next generation of microwave telescopes, such as the proposed CMB-S4 experiment, might be sensitive enough to detect these subtle signals, giving us another window into the pre-Bang cosmos. The study of high-energy cosmic rays offers yet another avenue. Particles with energies far beyond what human-made accelerators can produce constantly bombard Earth from space. Some theories suggest these ultra-high energy cosmic rays might originate from exotic processes in the early universe, potentially carrying information about pre-Big Bang physics. Observatories like the Pierre Auger Observatory in Argentina, which covers an area larger than Rhode Island, are designed to catch these rare cosmic messengers. Even black holes may hold clues to the universe's birth. Primordial black holes, hypothetical black holes, form not from collapsing stars but from density fluctuations in the earliest moments after the Big Bang, could have distinctive properties that reveal conditions before inflation. If we could detect these ancient black holes through their gravitational effects, or the radiation they emit as they evaporate, we might gain insights into the pre-inflationary universe. Some cosmologists have proposed that we might find evidence for a previous universe's existence in the distribution of galaxies and galaxy clusters. If our universe emerged from a bounce, subtle correlations might persist from before the bounce, imprinted in the large-scale structure of our cosmos. Advanced statistical techniques applied to data from galaxy surveys like the Dark Energy Survey might reveal these whispers from a previous cosmic cycle. The LIGO and Virgo gravitational wave observatories have already revolutionized astronomy by detecting merging black holes and neutron stars. Future space-based detectors like LISA will be sensitive to gravitational waves at different frequencies, potentially allowing us to hear the gravitational music from the universe's first moments. If certain pre-Big Bang theories are correct, these gravitational waves might carry echoes from before the Big Bang itself. The search for gravitational waves from the early universe parallels the search for the elusive B-mode polarization pattern in the cosmic microwave background. This particular polarization signature would be smoking gun evidence for primordial gravitational waves produced during inflation. The BICEP background imaging of cosmic extragalactic polarization experiment and others have been hunting for this signal for years. A definitive detection would not only confirm inflation, but potentially reveal details about pre-inflationary physics. As we push the boundaries of knowledge backward in time, we encounter profound philosophical questions alongside the scientific ones. If the universe had a beginning, what caused it? If it didn't have a beginning, how can an infinite past be physically realized? Is our concept of causality, that effects must follow causes, even applicable when discussing the origin of time itself? The ancient Greek philosopher Parmenides argued that nothing comes from nothing, a principle that still challenges our understanding of cosmic origins. Modern physics has transformed this debate by revealing that nothing in the quantum sense isn't really nothing at all. The quantum vacuum is a seething cauldron of virtual particles, fields, and fluctuations. Perhaps what we call nothing contains the seeds of everything. This connects to an even deeper question. Why does the universe exist at all? The physicist and philosopher David Deutsch suggests that the ultimate answer might not be found in physics, but in information theory. Perhaps the universe exists because it contains patterns that can encode information efficiently, a cosmos optimized for complexity and knowledge. In this view, the laws of physics might be selected not by some external design, but by an intrinsic principle that maximizes the universe's capacity for computation and information processing. Meanwhile, cosmologist Lee Smolin has proposed a controversial idea called cosmic natural selection. Perhaps universes reproduce through black holes, with each black hole creating a new universe with slightly different physical laws. Over cosmic generations, universes with physical constants that maximize black hole production would predominate, potentially explaining why our universe seems fine-tuned for complexity. This notion of cosmological evolution parallels biological evolution, suggesting that the apparent design in our universe emerges not from a designer, but from a selection process operating across a multiverse. Even as we contemplate these grand theories, we must remain humble about the limits of human knowledge. Throughout history, each generation has believed they were on the verge of a complete understanding of the cosmos, only to discover new layers of mystery. From Ptolemy's epicycles to Newton's clockwork universe to Einstein's curved spacetime, our models have grown increasingly sophisticated, yet the fundamental mystery of existence remains. The history of cosmology teaches us caution. For centuries, Western astronomers believed Earth was at the center of creation. Then Copernicus placed the sun at the center. Then we learned our sun is just one star among billions in the Milky Way. Then we discovered our galaxy is one among billions in the observable universe. With each step, our cosmic significance seemed to diminish, yet our capacity for understanding grew. Perhaps the pre-Big Bang question represents the next great decentering, revealing our universe to be just one chapter in a much grander cosmic story. The question of what happened before the Big Bang reminds us that science is not just about answers, but about asking better questions. Each theory, inflation, quantum cosmology, string theory, loop quantum gravity, represents a different conceptual framework for approaching the ultimate origin. Rather than competing descriptions, they might be complementary perspectives, each illuminating different aspects of the pre-Bang cosmos. The mathematical physicist Roger Penrose has proposed his own radical vision called conformal cyclic cosmology. In this model, the far future of one universe becomes the Big Bang of the next. As matter decays into radiation over unimaginably long timescales, the universe loses all its mass. With nothing but massless particles remaining, there's no way to measure time or distance. This makes the infinitely expanded end state of one universe mathematically identical to the infinitely compressed beginning of another, creating a natural cycle without beginning or end. Penrose claims to have found evidence for his theory in the cosmic microwave background, concentric circles that might be imprints of supermassive black hole collisions from a previous cosmic eon. While most cosmologists remain skeptical, the possibility highlights how observational data might eventually distinguish between these competing visions of pre-Bang physics. As we peer into the cosmic dawn, we confront the limits not just of our knowledge, but of knowledge itself. The origin of the universe may be fundamentally beyond complete human understanding, not because our minds are too limited, but because the question involves logical paradoxes that cannot be resolved within any consistent framework. Philosopher Immanuel Kant identified such paradoxes centuries ago in his Antinomies of Pure Reason, showing how pure reason leads to contradictions when applied to questions of cosmic origins. Yet this doesn't mean we should stop asking. The search for the universe's beginning has already revolutionized our understanding of physics, forcing us to develop quantum gravity, rethink the nature of time, and question our most basic assumptions about reality. The journey matters as much as the destination. Perhaps the most profound insight from modern cosmology is that the universe is not just a collection of objects in space, but a self-contained system of relationships evolving through time. Space and time themselves are dynamic participants in cosmic evolution, not just the stage on which it unfolds. The Big Bang wasn't an explosion in pre-existing space, but the beginning of space itself. This holistic perspective finds mathematical expression in the holographic principle, a strange implication of string theory. According to this principle, all the information contained in a region of space can be represented as information on the boundary of that region. Applied to cosmology, this suggests that our three-dimensional universe might be equivalent to a two-dimensional quantum system on its boundary. In such a picture, the Big Bang might be understood not as a temporal beginning, but as a particular configuration in this boundary description. Similarly, the ADS-CFT correspondence, a remarkable discovery in theoretical physics, suggests that certain quantum Penrose claims to have found evidence for his theory in the cosmic microwave background, concentric circles that might be imprints of supermassive black hole collisions from a previous cosmic eon. While most cosmologists remain skeptical, the possibility highlights how observational data might eventually distinguish between these competing visions of pre-bang physics. As we peer into the cosmic dawn, we confront the limits not just of our knowledge, but of knowledge itself. The origin of the universe may be fundamentally beyond complete human understanding, not because our minds are too limited, but because the question involves logical paradoxes that cannot be resolved within any consistent framework. Philosopher Immanuel Kant identified such paradoxes centuries ago in his Antinomies of Pure Reason, showing how pure reason leads to contradictions when applied to questions of cosmic origins. Yet this doesn't mean we should stop asking. The search for the universe's beginning has already revolutionized our understanding of physics, forcing us to develop quantum gravity, rethink the nature of time, and question our most basic assumptions about reality. The journey matters as much as the destination. Perhaps the most profound insight from modern cosmology is that the universe is not just a collection of objects in space, but a self-contained system of relationships evolving through time. Space and time themselves are dynamic participants in cosmic evolution, not just the stage on which it unfolds. The Big Bang wasn't an explosion in pre-existing space, but the beginning of space itself. This holistic perspective finds mathematical expression in the holographic principle, a strange implication of string theory. According to this principle, all the information contained in a region of space can be represented as information on the boundary of that region. As we venture beyond the boundaries of our observable universe, we confront perhaps the most mind-bending question in modern cosmology. Is our universe all that exists, or is it merely one bubble in a vast cosmic ocean? The multiverse hypothesis suggests that what we call the universe, all we can observe and measure, may be just a tiny fragment of a much larger and more diverse cosmic reality. This concept, once the domain of science fiction, has become a serious scientific proposal supported by several independent lines of theoretical physics and cosmology. The multiverse isn't a single theory, but a family of related ideas, each emerging from attempts to solve fundamental problems in physics. These range from explaining the peculiar fine-tuning of physical constants to resolving paradoxes in quantum mechanics and string theory. What unites these proposals is the revolutionary suggestion that reality is far more extensive and diverse than we can directly observe. Our universe, with its hundreds of billions of galaxies stretching across billions of light years, may be just one of countless others, each with its own physical laws, constants, and cosmic histories. The concept first gained scientific credibility through inflationary cosmology, the theory we explored in our previous discussion of the pre-Big Bang universe. Recall that inflation suggests the universe underwent a period of exponential expansion in its earliest moments. But the mathematics of inflation leads to a surprising conclusion. Once inflation begins, it likely never stops completely. While inflation ended in our observable patch of cosmos, allowing galaxies, stars, and planets to form, it continues in other regions, eternally spawning new universes through a process called eternal inflation. Imagine a vast, rapidly expanding sea of space-time, where quantum fluctuations occasionally create regions where inflation stops. Each of these regions becomes a separate universe like our own, with its own Big Bang, expansion, and subsequent evolution. These universes form like bubbles in a boiling pot, each one a self-contained cosmic system that may differ dramatically from our own. In this eternal inflation scenario, new universes are constantly being born, creating an endless cosmic landscape of distinct realities, expanding away from each other faster than light can travel between them. Physicist Andre Linde, one of eternal inflation's pioneers, describes it as a self-reproducing fractal, with new universes budding off existing ones in a never-ending process. Each universe may experience different spontaneous symmetry breakings as it cools, potentially resulting in different particles, forces, and fundamental constants. In this view, our universe is just one bubble with particular properties, surrounded by an infinite sea of other bubbles with different laws of physics. Linde calls this scenario the self-reproducing inflationary multiverse, and it represents one of the most developed multiverse theories in modern cosmology. A different type of multiverse emerges from quantum mechanics, specifically from attempts to interpret what happens during quantum measurement. The famous many worlds interpretation, proposed by physicist Hugh Everett in 1957, suggests that every quantum event creates a branching of reality into multiple worlds. When a quantum system that exists in a superposition of states is measured, instead of randomly collapsing into one outcome, as the Copenhagen interpretation suggests, reality splits into multiple branches, each containing one of the possible outcomes. If the many worlds interpretation is correct, then reality consists of an ever-branching tree of universes, splitting with every quantum interaction. Since quantum events happen constantly throughout the cosmos, the number of these parallel worlds would be unimaginably vast and continuously growing. In this view, there exist parallel versions of you who made slightly different decisions, worlds where historical events unfolded differently, and realities with every possible combination of quantum outcomes since the Big Bang. While these parallel worlds would occupy the same space-time as our own, they would be forever inaccessible to us, having decohered or separated from our branch of reality. String theory, humanity's most ambitious attempt to unify quantum mechanics and general relativity, provides yet another framework for a multiverse. According to string theory, fundamental particles are actually tiny, vibrating strings of energy, and the different vibration patterns determine the particle's properties. But the mathematics of string theory is consistent only if there are additional spatial dimensions beyond the three we experience, typically 6 or 7 extra dimensions curled up so tightly we cannot detect them. The way these extra dimensions are compactified, folded up into microscopic structures, determines the physics of the resulting universe. And here's where the multiverse enters. String theory doesn't predict a unique compactification. Instead, it allows for an astronomical number of different ways to fold these extra dimensions, perhaps 10 to the 500 different configurations, each creating a universe with different physical laws. This vast collection of possible universes is called the string theory landscape, and our universe would be just one valley in this immense cosmic terrain. Leonard Susskind, one of string theory's pioneers, argues that all these different possible universes actually exist somewhere in a grand multiverse. Our universe, with its particular forces, particles, and constants, is simply the one where conditions allowed for our existence. This is not simply speculation, but a potential solution to one of physics' most perplexing questions. Why do the fundamental constants of nature appear precisely tuned to allow for complex structures like galaxies, stars, and ultimately life? This fine-tuning problem has troubled physicists for decades. Consider the cosmological constant, the energy density of empty space that drives the universe's accelerating expansion. Its observed value is more than 120 orders of magnitude smaller than theoretical predictions. If it were slightly larger, the universe would have expanded too quickly for structures to form. If slightly smaller, the universe would have recollapsed before stars could evolve. This eerie precision appears in numerous physical constants, suggesting either an incredible coincidence, unknown physical principles, or a multiverse where all possible values exist somewhere. In a multiverse with diverse physical laws, intelligent observers would naturally find themselves in universes compatible with their existence. This concept, known as the anthropic principle, suggests that the apparent fine-tuning of our universe isn't necessarily evidence of design, but a selection effect. Just as we shouldn't be surprised to find ourselves on a planet with liquid water rather than a star's surface, perhaps we shouldn't be surprised to find ourselves in a universe where the physical constants allow atoms, stars, and biology to exist. The multiverse also emerges from theoretical attempts to explain cosmic inflation itself. The physics driving inflation requires a field called the inflaton to roll down from a high-energy state to a lower one, like a ball rolling down a hill. But the shape of this potential energy landscape could be complex, with multiple valleys representing different possible universes. Our universe would correspond to just one of these valleys, one possible way for inflation to end, while other valleys would produce universes with different physical properties. Beyond these science-based multiverse concepts, philosophers and cosmologists have proposed even more radical forms of cosmic plurality. Mathematician Max Tegmark has classified multiverses into 4 increasingly encompassing levels. Level 1 is simply regions beyond our cosmic horizon, parts of our same universe too far away to observe because light hasn't had time to reach us since the Big Bang. Level 2 includes the bubble universes of eternal inflation with potentially different physical constants. Level 3 encompasses the many worlds interpretation of quantum mechanics. But Level 4, the ultimate ensemble, suggests that any mathematically consistent set of physical laws might exist as an actual universe somewhere in the multiverse. At this extreme, the multiverse becomes the totality of all possible realities, defined by consistent mathematics. Physical existence and mathematical existence become equivalent. If true, our universe exists simply because the mathematical structure describing it is logically possible. This philosophical view, called mathematical Platonism, suggests that the fundamental nature of reality is mathematical rather than physical, an idea that reaches back to ancient Greek philosophers like Pythagoras and Plato. But how could we ever test such extraordinary claims? The multiverse hypothesis faces a profound challenge. If other universes are causally disconnected from our own, beyond our cosmic horizon or in different branches of quantum reality, can the multiverse ever be more than speculation? Critics argue that untestable theories fall outside the bounds of science, regardless of their mathematical elegance. Without empirical evidence, how do we distinguish between a scientifically valuable hypothesis and an unfalsifiable philosophical position? Proponents respond that indirect evidence might still be possible. For instance, certain versions of the multiverse make statistical predictions about our universe's properties. If our universe is one random sample from a particular ensemble of universes, certain features should be more likely than others. By comparing these predictions with observations, we might find support for specific multiverse models. For example, if our universe shows properties predicted to be common across a theorized ensemble, that would increase our confidence in that multiverse model. Another approach involves searching for signs of collisions between bubble universes in the cosmic microwave background. If our universe bubble collided with another bubble in its early history, this might have left detectable patterns in the ancient radiation that permeates space. Several research teams have analyzed cosmic microwave background data, looking for these signatures, though conclusive evidence remains elusive. Future missions with more sensitive instruments might reveal these subtle cosmic bruises, providing direct evidence for a bubble multiverse. String theory multiverses might be testable through precise measurements of fundamental forces. If string theory is correct, the compactification of extra dimensions should leave subtle imprints on how forces behave at extremely high energies. Future particle accelerators or cosmic ray observations might detect these string-theoretic effects, indirectly supporting the existence of the string landscape and its multiverse implications. Quantum multiverse theories face different experimental challenges. While we cannot directly observe parallel quantum worlds, certain experiments with quantum systems might distinguish between different interpretations of quantum mechanics. Quantum computers, which explicitly manipulate superpositions of quantum states, might eventually help determine whether the many worlds interpretation better explains quantum phenomena than other models. The multiverse concept also raises profound philosophical questions about identity, causality, and the nature of physical law. If all possibilities exist somewhere in the multiverse, what gives meaning to the specific reality we experience? Does the concept of probability still make sense if all outcomes actually occur in some universe? And if physical constants vary across different universes, are there deeper meta-laws governing the multiverse as a whole? The philosophical implications extend to questions of purpose and design. The multiverse provides a naturalistic explanation for cosmic fine-tuning, potentially eliminating the need for a cosmic designer. But some philosophers argue that the multiverse itself requires explanation. Why does this particular multiverse exist, rather than some other arrangement or nothing at all? The multiverse pushes the question of cosmic origins to a higher level, rather than eliminating it entirely. Religious and spiritual traditions have varied responses to multiverse concepts. Some see the multiverse as conflicting with their theological understanding of creation, while others find ways to incorporate cosmic plurality into their worldviews. Throughout history, humans have contemplated multiple worlds, from ancient Greek atomists who proposed infinite worlds to medieval scholastics who debated whether God could have created multiple universes. The scientific multiverse represents a modern approach to these age-old questions about the extent and nature of reality. For ordinary people, the multiverse can seem both exhilarating and disorienting. The possibility that every decision spawns alternative universes, where different choices were made, raises questions about personal identity and free will. If all possibilities exist somewhere in the multiverse, does that diminish the significance of our particular reality? Or does it place even greater importance on the unique branch of reality we inhabit and shape through our choices? Science fiction has long explored these themes, from parallel Earths, where history took different turns, to fully alien universes with different physical laws. Shows like Rick and Morty and films like Everything Everywhere All at Once have popularized multiverse concepts, reflecting our cultural fascination with paths not taken and lives unlived. The multiverse serves as a powerful metaphor for human wondering about alternatives and possibilities beyond our immediate experience. Yet we should remember that the scientific multiverse is not the same as these fictional portrayals. The bubble universes of eternal inflation would be completely distinct cosmological systems, not parallel Earths where you have a doppelganger with a different hair color. Even in the many worlds interpretation of quantum mechanics, the branching universes rapidly become unrecognizably different due to quantum butterfly effects. These aren't worlds we could visit with the right technology. They're causally disconnected realities that theoretical physics suggests must exist. The history of science teaches us humility about the boundaries of the possible. 500 years ago, the notion of billions of galaxies would have seemed as fantastical as the multiverse does to many today. As Einstein's theory of relativity predicted phenomena like black holes and gravitational waves long before we could detect them, current theories pointing to a multiverse may presage future discoveries that confirm aspects of cosmic plurality. Science advances by following the mathematics and evidence wherever they lead, even when they challenge our intuitive understanding of reality. Recent astronomical observations provide tantalizing hints that might indirectly support certain multiverse models. The discovery of the Higgs boson, with a mass of approximately 125 billion electron volts, places our universe in a potentially precarious position. According to calculations, This mass implies that our universe may be in a metastable state, where a quantum tunneling event could trigger a catastrophic vacuum decay, effectively destroying our universe as we know it. This precise value, balancing between stability and instability, is difficult to explain without appeal to either incredible fine-tuning or a multiverse, where all possible values of the Higgs mass exist in different bubble universes. Similarly, analyses of the cosmic microwave background radiation by the Planck satellite have found slight statistical anomalies that some physicists speculate might be evidence of our universe interacting with others before inflation ended. While mainstream interpretations attribute these patterns to random fluctuations or observational artifacts, they keep the door open to more exotic explanations involving cosmic collisions in a multiverse context. Black holes offer another potential connection to multiverse theories. Some speculative models suggest that the interiors of black holes might give birth to new universes, with the immense energy of collapse providing the conditions for a new cosmic inflation. In this scenario, each black hole in our universe could be the beginning of a new universe, inheriting some characteristics from our own, but developing its own distinct properties. This cosmological natural selection model, proposed by physicist Lee Smolin, suggests a kind of cosmic evolution where universes that produce many black holes have more offspring, leading to a multiverse dominated by universes with physical properties conducive to black hole formation. The concept of baby universes extends this idea further. In certain quantum gravity models, microscopic fluctuations in space-time could occasionally create tiny bubble universes that quickly disconnect from our own, expanding into their own independent realities. These quantum fluctuations would be too small to observe directly, but might influence the properties of our universe in subtle ways that future experiments could potentially detect. The mathematics of string theory continues to provide additional support for multiverse models. The discovery of dualities, mathematical equivalences between seemingly different string theories, suggests that what appear to be distinct universes might actually be different perspectives on the same underlying reality. The ADI-SAS-CFT correspondence, which relates gravity in curved spacetime to quantum field theory on its boundary, points to a profound holographic principle that could help us understand how different universes within the multiverse might be connected at a deeper level. Recent developments in quantum information theory also provide new perspectives on the multiverse. Some researchers propose that reality might be fundamentally informational rather than material, with different universes representing different possible configurations of information. This it from bit paradigm, championed by physicist John Wheeler, suggests that the physical universe emerges from more fundamental information theoretic principles, potentially explaining both quantum mechanics and the multiverse in a unified framework. Artificial intelligence and advanced simulations offer another angle on multiverse concepts. As our ability to create complex simulated worlds increases, some philosophers like Nick Bostrom have suggested that our reality might itself be a simulation created by advanced beings. If this simulation hypothesis is correct, then our universe would be just one of potentially countless simulated realities, a different kind of multiverse with its own philosophical implications. While this idea might seem far-fetched, it raises serious questions about the nature of reality and consciousness that overlap with more conventional multiverse theories. The boundaries between different multiverse concepts can sometimes blur. For example, the many worlds interpretation of quantum mechanics might be connected to the string theory landscape, if quantum events can influence which vacuum state a region of spacetime settles into. Similarly, eternal inflation and quantum many worlds might be different perspectives on the same underlying phenomenon, with quantum fluctuations driving the creation of new inflationary bubbles. These connections suggest that a unified theory of the multiverse might eventually emerge, incorporating elements from different approaches into a coherent framework. Critics of the multiverse often cite Occam's razor, the principle that explanations should not multiply entities unnecessarily. Isn't it simpler to assume just one universe rather than infinitely many? Proponents counter that the multiverse actually provides a simpler explanation at a deeper level. A single set of fundamental meta-laws that generates a multiverse might be mathematically simpler than specific laws fine-tuned to produce exactly our universe. In this view, the apparent complexity of the multiverse actually emerges from deeper simplicity, just as the vast complexity of life emerges from the relatively simple rules of chemistry and natural selection. The debate about multiverse theories intersects with broader questions about scientific methodology. Traditional science relies on testable hypotheses and empirical verification, but when dealing with concepts that push against the limits of observation, like multiverses or the interiors of black holes, scientists must sometimes rely more heavily on mathematical consistency, theoretical elegance, and indirect evidence. This tension between empiricism and theoretical inference characterizes much of contemporary fundamental physics, with multiverse theories representing perhaps the most extreme example of theory outpacing direct observation. Yet history shows that seemingly untestable theories can eventually find experimental support. Einstein's general relativity made predictions about gravitational waves that weren't directly confirmed until nearly a century later. The atomic theory was considered speculative for decades before technological advances provided direct evidence. Perhaps future technologies or observational techniques will similarly transform multiverse theories from philosophical speculation to empirically supported science. As we await such developments, the multiverse remains a powerful organizing principle for understanding various puzzles in fundamental physics. It provides potential explanations for the fine-tuning of physical constants, the specific properties of dark energy, the peculiarities of inflation, and the diversity of possible solutions in string theory. Rather than invoking extraordinary coincidences or mysterious design, the multiverse offers a natural framework within which our universe's specific features make sense. For cosmologists and physicists, the multiverse represents both a challenge and an opportunity. It challenges us to develop new theoretical tools and observational strategies to test ideas that seem to transcend our observable reality. It offers an opportunity to address profound questions about cosmic origins, physical laws, and our place in reality that might otherwise remain perpetually beyond scientific reach. Whether the multiverse ultimately proves to be a crucial insight into nature's deepest workings or a beautiful mathematical mirage, exploring its possibilities pushes science toward its fundamental limits. As we conclude our exploration of the multiverse hypothesis, we're left with a profound sense of cosmic possibility. Our universe, vast beyond human comprehension, with its hundreds of billions of galaxies stretching across billions of light years, might be just one bubble in an infinite cosmic ocean, one branch on an ever-growing quantum tree, or one valley in a landscape of string theory possibilities. While direct evidence remains elusive, the theoretical case for some form of multiverse grows stronger as physicists develop a deeper understanding of cosmic inflation, quantum mechanics, and string theory. Perhaps the ultimate significance of the multiverse lies not just in its scientific implications, but in how it transforms our cosmic perspective. Throughout history, humans have repeatedly discovered that reality is larger and more diverse than previously imagined. From ancient geocentric models to the modern understanding of billions of galaxies, the multiverse represents the next horizon in this cosmic journey, suggesting that even our entire observable universe might be just a tiny fragment of a far grander reality. As we peer beyond the boundaries of our observable cosmos, we confront perhaps the greatest question of all. Are we alone in reality, or is our universe just one among countless others in an infinite cosmic plurality? In the pantheon of cosmic mysteries, few objects inspire as much awe and scientific curiosity as black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. These cosmic abysses represent the most extreme environments in our universe, where the laws of physics are pushed to their breaking point and our understanding of reality is fundamentally challenged. Once considered mathematical curiosities, black holes have moved from theoretical prediction to observational certainty, yet they continue to guard their deepest secrets behind veils of darkness that modern science is only beginning to penetrate. Our journey to understanding black holes began in 1783, when English clergyman and amateur scientist John Michell first proposed the concept of what he called dark stars. Objects so massive that light itself would be trapped by their gravitational pull. The idea remained a curiosity until 1915, when Albert Einstein's general theory of relativity provided the mathematical framework to describe how mass warps the fabric of space-time. Shortly thereafter, German physicist Karl Schwarzschild, while serving on the Russian front during World War I, solved Einstein's equations for a simplified case, discovering what we now recognize as the mathematical description of a black hole, a solution that Einstein himself initially found too bizarre to be physically real. For decades, these strange solutions to Einstein's equations were considered mathematical abstractions rather than actual physical objects. The term black hole wasn't even coined until 1967, when American physicist John Wheeler used it during a lecture to describe these collapsed stars. The scientific community remained skeptical until the 1970s, when astronomers discovered Cygnus X1, a powerful X-ray source that appeared to be a massive star orbiting an invisible companion, the first observational evidence of a black hole. Today, we know the universe is teeming with these cosmic predators, from stellar mass black holes formed from collapsed stars to supermassive behemoths lurking at the centers of galaxies, including our own Milky Way. The defining feature of a black hole is its event horizon, the boundary beyond which nothing can return to the outside universe. This isn't a physical surface, but a one-way membrane in the fabric of space-time itself. Cross this invisible boundary, and you're forever cut off from the rest of the universe. Time and space behave so strangely near the event horizon that an outside observer watching someone fall into a black hole would see them appear to slow down, freeze in place, and gradually redshift into invisibility, while the falling person would experience time normally, crossing the event horizon without noticing any particular boundary. This stark difference between perspectives highlights how black holes distort the very fabric of reality. But what happens once you cross this cosmic point of no return? According to classical general relativity, all matter that falls into a black hole is inevitably crushed toward a central point of infinite density called a singularity. At this singularity, space-time curvature becomes infinite, and the laws of physics as we understand them break down completely. It's a place where quantum effects and gravitational forces both become overwhelmingly important, requiring a theory of quantum gravity that we don't yet possess. This central singularity represents one of the greatest unsolved problems in theoretical physics, a place where our most successful theories simply fail to provide answers. The singularity's nature is further complicated by cosmic censorship, a hypothesis proposed by mathematician Roger Penrose that suggests nature always hides singularities behind event horizons, preventing them from being observed from the outside universe. Yet some theoretical models suggest the possibility of naked singularities that aren't shrouded by event horizons, potentially allowing the weird physics of the singularity to affect the broader universe. If such objects exist, a prospect most physicists consider unlikely but cannot definitively rule out, they would profoundly challenge our understanding of causality and predictability in the cosmos. One of the most perplexing aspects of black hole physics is the information paradox, first identified by Stephen Hawking in the 1970s. Quantum mechanics insist that information can never be truly destroyed, merely scrambled, yet black holes seem to erase information about everything that falls into them, eventually radiating away as completely featureless Hawking radiation. This fundamental conflict between quantum mechanics and general relativity has driven decades of theoretical work, with proposed resolutions including information encoded in subtle correlations in the radiation, information stored in theoretical fuzzballs that replace the singularity, or exotic quantum effects that prevent true event horizons from forming in the first place. Hawking radiation, the theoretical process by which black holes can slowly evaporate, represents one of the most profound insights into black hole physics. In 1974, Hawking showed that quantum effects near the event horizon cause black holes to emit radiation as if they were thermal bodies, with a temperature inversely proportional to their mass. This means that black holes aren't completely black. They glow with an incredibly faint radiation, gradually losing mass in the process. A stellar mass black hole would take more than 10 to the power of 67 years to evaporate, far longer than the current age of the universe. But the theoretical implications are enormous, suggesting that black holes are thermodynamic objects with entropy and temperature, connecting gravity, quantum theory, and information in profound ways. The entropy of a black hole is particularly mysterious. According to Hawking's calculations, a black hole's entropy is proportional to its surface area, not its volume, as if all the information about what's inside is somehow encoded on the event horizon itself. This insight led to the holographic principle, a revolutionary idea suggesting that all the information contained in a volume of space can be represented as information on its boundary. In the context of black holes, this means that everything that falls in might be completely encoded on the event horizon, preserved rather than destroyed. This principle has profound implications beyond black holes, suggesting that our three-dimensional reality might fundamentally be a projection of information stored on a distant two-dimensional surface, a concept that has transformed theoretical physics. Black holes also challenge our understanding of time. Near the event horizon, time dilation becomes extreme. A clock falling into a black hole would appear to tick ever more slowly from an outside perspective, effectively freezing at the horizon itself. But from the perspective of someone falling in, time flows normally, and the horizon is crossed without incident. Inside the black hole, space and time effectively switch roles. Just as we inevitably move forward in time in the outside universe, anything inside a black hole inevitably moves toward the central singularity. The future isn't just predetermined, it's literally a place, the singularity at the center, which all paths within the black hole ultimately lead to. While stellar mass black holes form from collapsed stars, the origins of supermassive black holes, monsters millions or billions of times the mass of our sun that sit at the centers of most large galaxies, remain mysterious. These cosmic titans existed less than 1 billion years after the Big Bang, giving them seemingly insufficient time to grow to their observed sizes through conventional processes. Some theories suggest they formed from the direct collapse of massive gas clouds in the early universe, bypassing the stellar phase entirely. Others propose that primordial black holes created in the first moments after the Big Bang could have served as seeds. Understanding their formation and growth is crucial for comprehending galactic evolution, as these supermassive black holes appear to co-evolve with their host galaxies through mechanisms we're only beginning to unravel. The relationship between black holes and their host galaxies presents one of astronomy's most intriguing puzzles. There's a remarkably tight correlation between a galaxy's central black hole mass and the velocity dispersion of stars in its bulge, a relationship so precise it suggests black holes and galaxies must somehow regulate each other's growth. Black holes can profoundly influence their surroundings through jets and outflows, structures that extend for thousands of light years, heating intergalactic gas and potentially preventing it from cooling and forming new stars. This feedback process may explain why we don't see galaxies larger than a certain size, and highlights how these cosmic monsters, despite occupying a tiny fraction of a galaxy's volume, can shape cosmic evolution on the largest scales. Our understanding of black holes took a quantum leap forward in April 2019 when the Event Horizon Telescope collaboration released the first direct image of a black hole. Specifically, the supermassive black hole, at the center of Galaxy M87 This extraordinary technical achievement, combining data from radio telescopes across the globe to create a virtual Earth-sized telescope, revealed the shadow of the black hole's event horizon silhouetted against the glowing gas of its accretion disk. The image, showing a bright ring of light bent around the black hole's tremendous gravity, provided striking visual confirmation of Einstein's general relativity in the most extreme gravitational environment we can observe. 2 years later, the same collaboration released polarization data from the same black hole, revealing the structure of magnetic fields around it and providing new insights into how these objects launch powerful jets into intergalactic space. Black holes are not merely passive cosmic traps. They are among the most energetic objects in the universe. When matter falls toward a black hole, it typically forms an accretion disk, a flattened spiraling structure of gas and dust that heats to millions of degrees through friction and compression. These superheated accretion disks can outshine entire galaxies, particularly in objects called quasars, active galactic nuclei powered by supermassive black holes consuming matter at prodigious rates. Some of this infalling material doesn't actually reach the black hole, but is channeled into jets, narrow beams of particles accelerated to near the speed of light that blast out from the black hole's poles, extending for thousands or even millions of light years into intergalactic space. The mechanism that powers these jets remains not fully understood, but magnetic fields almost certainly play a crucial role. As gas spirals into the black hole, magnetic field lines are thought to twist and concentrate, creating a kind of electromagnetic tornado that channels plasma along the black hole's rotation axis. These jets can dramatically impact their surroundings, heating the intergalactic medium and potentially influencing star formation across entire galaxy clusters. When these jets happen to point toward Earth, we observe them as blazars, some of the most luminous sustained objects in the universe, outshining 1 trillion suns and visible across billions of light years of cosmic space. In 2015, another breakthrough in black hole science occurred when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from the merger of 2 black holes over 1 billion light-years away. This historic observation not only confirmed a major prediction of Einstein's general relativity, but also opened an entirely new window on black hole physics. In the years since, dozens of black hole mergers have been detected, allowing astronomers to catalogue black holes across a range of masses and study how they dance together before merging. Particularly intriguing are the masses of these merging black holes. Some fall into unexpected mass ranges, challenging our understanding of stellar evolution and black hole formation. When black holes merge, they release more energy in gravitational waves than all the stars in the observable universe emit as light. Yet they do so in a fraction of a second. This makes black hole mergers the most energetic events we know of in the current universe. The gravitational waves from these cataclysmic events stretch and compress space-time itself as they propagate across the cosmos, causing minute changes in distance that LIGO and other detectors measure using laser interferometry. Future space-based detectors like LISA will be able to detect mergers of supermassive black holes, events that make stellar mass mergers look tiny by comparison, and that likely occurred frequently in the early universe as galaxies collided and combined. Black holes can also form binaries with normal stars, creating systems where the black hole steadily consumes its stellar companion. These X-ray binaries, as astronomers call them, provide some of our best laboratories for studying black hole physics. By observing how material from the companion star spirals into the black hole, researchers can probe the warped spacetime near the event horizon. In some cases, these systems can produce relativistic jets, similar to those seen in active galactic nuclei, but on a smaller scale. The first confirmed black hole, Cygnus X1, is such a system, where a black hole approximately 15 times the mass of our Sun is stripping material from a blue supergiant companion. Perhaps the most tantalizing frontier in black hole research involves the potential connection between black holes and wormholes. hypothetical tunnels through space-time that could potentially connect distant regions of the universe or even different universes. Einstein's equations allow for such structures, and some theoretical models suggest that the interiors of certain black holes could connect to white holes, objects that can only expel matter and energy, never absorb it. If such black hole/white hole pairs exist, they could theoretically form traversable wormholes. While the physics required to keep such wormholes open likely violates energy conditions in general relativity, they remain a fascinating theoretical possibility that pushes the boundaries of our understanding of space-time. The exotic physics of black holes extends to their potential role in fundamental physics. Some theories propose that microscopic black holes could have formed in the extreme conditions of the early universe. These primordial black holes, if they exist, could account for some or all of the mysterious dark matter that appears to dominate the mass of the universe. Unlike stellar black holes, primordial black holes could potentially have masses much smaller than that of our Sun, even as small as a mountain or less. The smallest of these would have long since evaporated through Hawking radiation, potentially leaving subtle imprints on the cosmic microwave background or other cosmological observables that future observations might detect. Black holes may even play a role in the eventual fate of the universe. In the far, far future, after all, stars have burnt out, and all matter has either been ejected from galaxies or fallen into black holes. The universe will be dominated by black holes gradually evaporating through Hawking radiation. This black hole era would last an unimaginably long time, perhaps 10 to the power of 100 years, during which these cosmic leviathans would slowly return their mass energy to the universe as extremely dilute radiation. Eventually, even the supermassive black holes will evaporate, leaving behind a cold, diffuse soup of fundamental particles unless new physics intervenes or quantum fluctuations trigger another inflationary epoch, potentially restarting the cosmic cycle. On the theoretical frontier, black holes have become central to one of the most important quests in fundamental physics, the reconciliation of quantum mechanics and general relativity. These two pillars of modern physics, extraordinarily successful in their respective domains, come into direct conflict in the extreme conditions near a black hole's singularity. Various approaches to quantum gravity, including string theory, loop quantum gravity, and others, are being tested against the theoretical laboratory that black holes provide. Some propose that the singularity is replaced by an exotic quantum structure. Others suggest that space-time itself emerges from more fundamental quantum entities. Black holes may hold the key to a unified theory that would transform our understanding of space, time, and matter at the most fundamental level. The future of black hole research looks extraordinarily promising as new observational tools come online. The next generation of gravitational wave observatories will detect thousands of black hole mergers, building a census of these objects across cosmic history. Advanced very long baseline interferometry will produce increasingly detailed images of black hole shadows, potentially revealing their spin and other properties. X-ray telescopes with unprecedented sensitivity will probe the superheated plasma swirling just outside event horizons. Together, these observations will test general relativity in the strong field regime, potentially revealing deviations that could point to new physics beyond Einstein's century-old theory. For all our progress, we must acknowledge how much remains unknown about these cosmic enigmas. We haven't definitively resolved the information paradox or determined what happens at the singularity. We don't fully understand how supermassive black holes form or how they launch their powerful jets. We don't know if primordial black holes exist or if black holes connect to other universes. These mysteries remind us that black holes stand at the frontier of human knowledge, places where our most successful theories break down and new physics awaits discovery. They are cosmic laboratories for testing our most fundamental ideas about the nature of reality itself. The study of black holes transcends mere astronomical curiosity. When we probe these darkest corners of the cosmos, we're exploring the limits of physical law and the nature of space and time themselves. Black holes remind us that the universe is stranger and more wondrous than our intuition suggests. Governed by mathematics that reveals realities our evolved senses never prepared us to perceive directly. They challenge us to expand our conception of what's possible and to recognize that the cosmos may be not only queerer than we suppose, but queerer than we can suppose, to paraphrase biologist J.B. Haldane. As we continue our cosmic journey beyond these light-trapping monsters, we turn to another class of mysteries, unexplained phenomena from across the universe that continue to baffle astronomers and challenge our understanding of cosmic processes. While black holes represent well-established objects whose mysteries lie in their extreme physics, these next enigmas are observations and discoveries that don't yet fit neatly into our cosmic understanding. Phenomena that might require new physics, previously unknown natural processes, or even, in the most speculative scenarios, evidence of intelligence beyond Earth. The cosmos is not only a theatre of known wonders, but a landscape of continuing discovery, where new mysteries emerge even as old ones yield to human ingenuity and technological advancement. Beyond the relatively understood mysteries of dark matter, dark energy, and black holes, lies a collection of cosmic phenomena that truly push the boundaries of our scientific understanding. These are observations that either defy conventional explanation or that fit only awkwardly into our current theoretical frameworks. Cosmic puzzles that continue to baffle astronomers and physicists despite our best efforts to explain them. Some may eventually find resolution within existing physics, while others might require fundamental revisions to our understanding of the universe. In this cosmic cabinet of curiosities, we find phenomena ranging from enigmatic radio bursts that traverse billions of light years to strange structures on the largest scales of the observable universe. Among the most discussed cosmic mysteries of the past decade are fast radio bursts, FRBs, incredibly powerful pulses of radio energy that last for just milliseconds yet release as much energy as our sun produces in decades. First discovered in 2007 by astronomers combing through archival data from the Parkes Radio Telescope in Australia, these brief flashes appeared to originate from far beyond our galaxy, suggesting almost inconceivably powerful sources. For years, their exact origins remained entirely unknown, with theories ranging from the relatively mundane, flaring neutron stars, to the exotic, evaporating black holes, to the speculative, alien transmissions. After more than a decade of intensive study, astronomers have begun to solve parts of the FRB mystery. Some bursts have been traced to their host galaxies, and a few have even been found to repeat, ruling out cataclysmic one-time events as the explanation for at least some FRBs. A breakthrough came in April 2020, when astronomers detected a powerful radio burst from within our own Milky Way, associated with a magnetar, a highly magnetized neutron star. This suggested that at least some FRBs are produced by magnetar flares, extreme magnetic reconnection events that release enormous amounts of energy in a brief flash. Yet questions remain. Are all FRBs produced by magnetars? Why do some repeat, while others don't? Another enduring cosmic mystery is the Great Attractor, a concentration of mass equivalent to tens of thousands of galaxies that appears to be pulling our Milky Way, along with all neighboring galaxies, toward a specific region in space at an extraordinary velocity of about 600 kilometers per second. First identified in the 1970s through studies of galactic peculiar motions, this gravitational anomaly lies approximately 150 million light-years away in the direction of the constellations Triangulum Australe and Norma. What makes the Great Attractor particularly mysterious is that it sits in a region obscured by the plane of our own galaxy, the so-called zone of avoidance, where dust and stars in the Milky Way block our view of what lies beyond. Infrared and X-ray observations have gradually penetrated this cosmic blind spot, revealing that the Great Attractor contains several rich galaxy clusters, including the massive Norma cluster. But even these visible structures don't seem sufficient to explain the observed gravitational pull. Further studies revealed that the Great Attractor itself is being pulled toward an even larger mass concentration, the Shapley supercluster, lying about 400 million light-years away and containing over 30 galaxy clusters. This entire system forms part of a vast cosmic web of filaments, clusters, and superclusters that represents the largest known structure in the universe. On the opposite end of the cosmic density spectrum lie the cosmic voids, enormous regions of space, sometimes hundreds of millions of light-years across, that contain far fewer galaxies than expected. The largest known void, the Oort void, spans a mind-boggling 330 million light-years and contains just a few dozen galaxies where thousands would be expected in typical cosmic volume. These cosmic deserts were discovered in galaxy surveys beginning in the 1980s, but their extreme emptiness remains difficult to explain with standard cosmological models. While the formation of some emptiness is expected through the natural clustering of matter over cosmic time, the observed voids are emptier and larger than simulations predict. What makes cosmic voids particularly valuable is that they serve as enormous low-density laboratories for testing theories of gravity and dark energy. In regions nearly devoid of matter, the repulsive effect of dark energy should be more pronounced, potentially accelerating the expansion of these regions faster than the universe as a whole. Precise measurements of how light travels through these voids could therefore provide valuable constraints on dark energy models. Far from being merely empty space, these cosmic voids might hold important clues to fundamental physics and the large-scale structure of the universe. Among the most perplexing astronomical discoveries in recent decades is the phenomenon of rogue planets, planetary mass objects that orbit the galaxy directly, unattached to any star. Conventional planetary formation theory suggests that planets form within protoplanetary disks surrounding young stars, making these solitary wanderers difficult to explain. Some may have formed like stars through the direct collapse of molecular cloud material, but most are thought to be former planetary system members that were gravitationally ejected during chaotic early system evolution. What's remarkable is their potential abundance. Some theoretical models suggest there could be billions or even trillions of these nomadic worlds drifting through our galaxy alone, potentially outnumbering stars. Detecting these dark, cold objects presents enormous observational challenges as they emit almost no light of their own. The primary methods for finding them involve gravitational microlensing, detecting the brief brightening of background stars as the rogue planet's gravity bends their light, or direct infrared detection of the faint heat these objects still radiate. The few confirmed rogue planets raise intriguing questions. Could some harbor moons that might retain heat through tidal forces, potentially providing environments for subsurface life far from any star? Might our own solar system have ejected planets during its formation? The mysterious WOW signal detected by the Big Ear Radio Telescope on August 15, 1977, remains one of the most tantalizing potential extraterrestrial transmissions ever recorded. For 72 seconds, astronomer Jerry Ehman observed a signal 30 times stronger than the background noise, appearing exactly in the frequency range where radio astronomers had speculated alien civilizations might transmit, near the hydrogen line at 1.42 GHz. The signal's characteristics, a gradual rise and fall in intensity matching what would be expected from a celestial source passing through the telescope's beam, suggested it came from beyond Earth. So struck was Ehman by the signal's unusual strength and appearance that he circled the printout and wrote, "Wow," in the margin. Despite repeated attempts over more than 4 decades, the WOW signal has never been detected again, making its origin impossible to confirm. Natural explanations have been proposed, including comets with hydrogen clouds, unusual stellar activity, or even reflections of Earth signals off space debris. Yet none fully satisfy all the observed characteristics. The signal remains one of the strongest candidates for an extraterrestrial transmission, though far from conclusive proof. If it was indeed a transmission from another civilization, it appears to have been a brief one. raising the possibility that any eventual contact with extraterrestrial intelligence might be similarly fleeting and hard to verify. Among the strangest objects in astronomy are the so-called Tabby's star, officially known as KIC 8462852, whose unprecedented dimming behavior has challenged conventional astronomical explanation. Discovered through the Kepler Space Telescope's hunt for exoplanets, this otherwise ordinary F-type star exhibited bizarre brightness fluctuations, sometimes dimming by up to 22% for days at a time, in irregular, non-repeating patterns. These dimming events were far too substantial to be explained by planets crossing the star's face and lacked the regularity that would be expected from orbiting objects. When first reported in 2015 by astronomer Tabitha Boyajian, the star's behavior was so unusual that even serious scientists briefly considered the possibility of alien megastructures. Further observations have pointed toward more natural, if still puzzling, explanations involving dust. Analysis of different wavelengths during dimming events suggests that fine dust surrounding the star is the most likely culprit, rather than solid objects. But the source of this dust remains unclear. Leading hypotheses include the aftermath of a massive collision in the star's planetary system, a disintegrating moon around a planet, comets broken apart by the star's gravity, or even interstellar dust clouds coincidentally passing between us and the star. While the alien megastructure hypothesis has faded, Tabby's star continues to represent a case where a seemingly normal star behaves in ways our current stellar models simply didn't predict. Perhaps no cosmic structures are as visually striking and theoretically perplexing as polar ring galaxies, rare systems where a ring of gas, dust, and stars orbits perpendicular to the main disk of the galaxy. The most famous example, NGC 4650, looks like a cosmic bullseye, a flattened spiral galaxy with a nearly perfect ring encircling it at right angles. These peculiar formations are thought to result from galactic collisions, where a larger galaxy strips material from a gas-rich donor galaxy passing nearby. What makes these systems particularly valuable to astronomers is that they serve as natural laboratories for studying dark matter. The two perpendicular rotating structures experience the galaxy's gravitational field from different orientations, allowing astronomers to construct three-dimensional maps of the invisible dark matter halo surrounding the galaxy. One of modern astronomy's most puzzling discoveries is the ultra-diffuse galaxy population, enormous galaxies, with the mass and star count of dwarf galaxies, but spread across volumes as large as the Milky Way. First identified in significant numbers around 2015, these cosmic ghosts are extremely difficult to detect due to their incredibly low surface brightness. Their stars are spread so thinly that the galaxies are nearly transparent, visible only with the most sensitive telescopes. What makes these galaxies particularly baffling is their very existence. Standard galaxy formation models struggle to explain how such diffuse structures could form and survive. Their low density should make them extraordinarily vulnerable to being torn apart by interactions with other galaxies, yet they somehow persist. Adding to the mystery, detailed studies of some ultra-diffuse galaxies reveal wildly different properties. Some appear to contain almost no dark matter, contradicting the standard picture where dark matter forms the gravitational scaffold around which galaxies form. Others seem to be almost entirely dark matter, with far fewer stars than would be expected for their mass and size. One particularly perplexing example, Dragonfly 44, appears to have the mass of the Milky Way, but only 1% as many stars, suggesting it might be 999 parts dark matter to 1 part visible matter. These galaxies challenge our understanding of how galaxies form and evolve, suggesting either that conventional theories are missing important physics, or that galaxies can form through multiple different pathways. Astronomical surveys of the distant universe occasionally turn up objects that defy easy classification within our understanding of cosmic evolution. In 2015, astronomers discovered an object designated WISE-J 2245-0538, a galaxy shining with the light of 300 trillion suns, making it the most luminous galaxy known. This extraordinary brightness comes from a central supermassive black hole, consuming matter at rates that push against the theoretical limits, creating an accretion disk so hot and bright that it outshines all the stars in the galaxy combined. What's particularly baffling is how this black hole grew large enough to power such extreme activity in the available cosmic time, and how it can sustain an accretion rate that seems to exceed what physical models suggest is possible. Similarly puzzling are the green pea galaxies, compact systems with incredibly high rates of star formation that appear as small, round, green dots in optical images. Their unusual color comes from extremely strong oxygen emission lines, indicating intense star formation and the resulting energetic radiation ionizing the surrounding gas. These cosmic oddities are forming stars at rates hundreds of times higher than the Milky Way, despite their small size. And they may represent a previously unrecognized phase of galaxy evolution, or a rare pathway that only some galaxies follow. They also share intriguing similarities with the earliest galaxies that formed after the Big Bang, potentially providing nearby laboratories for studying how the first galaxies ionized the early universe. Among the most recently discovered cosmic mysteries are the so-called odd radio circles, ORCs. Enormous rings of radio emission spanning millions of light years that don't seem to correspond to any known type of astronomical object. First identified in 2019 using the Australian Square Kilometre Array Pathfinder telescope, these perfect circles of radio emission have no obvious optical, infrared or X-ray counterparts, making their nature difficult to determine. Only a handful have been detected so far, but they may represent an entirely new class of astronomical object. Current hypotheses include the radio lobes of galaxies seen end-on, the result of vast shockwaves from cataclysmic events like galaxy mergers, or even the throats of wormholes, though this last explanation remains highly speculative. At the very largest scales of cosmic structure, several anomalies continue to challenge our understanding of how the universe evolved after the Big Bang. The axis of evil is a controversial pattern in the cosmic microwave background radiation, where temperature fluctuations appear to align with the plane of our solar system, something that should be extremely improbable in a universe where all directions are supposed to be equivalent. Similarly, structures like the Giant Ring, a ring of galaxies nearly 5 billion light-years across, and the Great Wall, a filament of galaxies stretching more than 1.5 billion light-years, appear to exceed the maximum size that should be possible given the age of the universe and the speed at which gravitational assembly can occur. The cosmos also presents us with timing puzzles, events that seem to be occurring at suspicious moments in cosmic history. The why now problem of dark energy asks why cosmic acceleration began relatively recently in cosmic history, just as complex structures like galaxies, stars, and planets were forming. This apparent coincidence, where humans exist at a time when both matter and dark energy significantly influence cosmic evolution, seems suspiciously fortuitous. Similarly, the fact that we live at a time when the angular size of the Moon and Sun are almost exactly the same in Earth's sky, allowing for perfect solar eclipses, represents another temporal coincidence that has no obvious physical explanation. Some of the most perplexing astronomical observations involve transient phenomena, events that appear briefly and then vanish, making them difficult to study systematically. In 1909, Arctic explorer Robert Peary reported seeing a momentary flash on the dark side of Venus, an observation occasionally repeated by others over the decades, but never explained or systematically confirmed. Similarly, amateur and professional astronomers occasionally report brief flashes of light on the Moon's surface, transient lunar phenomena, or MARS, some lasting mere seconds. Even on much larger scales, astronomical surveys sometimes capture brief flashes or bursts of radiation with no obvious source or explanation. The transient nature of the cosmos, where violent events can occur in an instant after millions of years of apparent stability, means that some of its most interesting phenomena may be the hardest to study. The history of astronomy teaches us humility about cosmic mysteries. Many phenomena once considered inexplicable, from pulsars to quasars to gamma-ray bursts, eventually yielded to scientific investigation as our observational tools and theoretical understanding improved. Yet this same history suggests that the resolution of current mysteries will likely lead to deeper questions and new enigmas. Each answered question tends to spawn multiple new lines of inquiry, as we realize that our previous conception of the problem was incomplete. The cosmic phenomena that puzzle astronomers today represent not failures of the scientific enterprise, but opportunities, places where nature is revealing something unexpected about the fundamental workings of the universe. As our observing capabilities continue to advance, with new facilities like the James Webb Space Telescope, the Vera C. Rubin Observatory, and the Square Kilometre Array coming online, many current mysteries will likely find resolution. Each new generation of telescopes has revealed the universe to be richer and more complex than previously imagined. Yet, if history is any guide, these same instruments will uncover entirely new categories of unexplained phenomena, ensuring that the cosmic puzzle never becomes fully solved, but merely transforms into new and deeper questions. The enduring message of these cosmic mysteries is not that the universe is fundamentally incomprehensible, but that it is inexhaustibly interesting, a source of wonder and discovery without end. This endless frontier of discovery leads us naturally to one of the greatest cosmic mysteries of all. Are we alone in the universe? The apparent absence of evidence for other technological civilizations, despite the vast number of potentially habitable worlds, constitutes the famous Fermi Paradox, which we'll explore in our next section. The unexplained phenomena we've discussed, from fast radio bursts to the wow signal, occasionally intersect with this greater question of extraterrestrial intelligence. While most cosmic mysteries likely have natural explanations, the possibility that some might represent the artifacts or communications of advanced civilizations cannot be dismissed entirely. As we turn to the Fermi Paradox, we'll examine the profound puzzle of why, in a galaxy of hundreds of billions of stars and potentially trillions of planets, we have not yet detected definitive evidence of other technological civilizations. In the summer of 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory when the conversation turned to extraterrestrial life. After discussing the vastness of the universe and the probability that other technological civilizations must exist, Fermi famously asked, "Where is everybody?" This simple question crystallized what has become one of science's most profound paradoxes. Given the extraordinary size and age of the universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars and potentially trillions of planets, why haven't we found evidence of other technological civilizations? The mathematical certainty that extraterrestrial intelligence should exist seems irreconcilable with the conspicuous absence of evidence for such beings. This disconnect between expectation and reality has become known as the Fermi Paradox, and it continues to challenge our understanding of our place in the cosmos. The paradox begins with numbers so vast they strain comprehension. Our Milky Way galaxy alone contains between 200 billion and 400 billion stars. Recent discoveries from NASA's Kepler mission and other projects have established that planets are not rare exceptions but the norm, with most stars hosting planetary systems. Conservative estimates suggest there are at least 100 billion planets in our galaxy, with several billion of these located in what astronomers call the habitable zone, the region around a star where temperatures could allow liquid water to exist on a planet's surface. Meanwhile, the observable universe contains at least 2 trillion galaxies, each with their own vast stellar populations. If even a tiny fraction of habitable planets eventually develop intelligent life, the universe should be teeming with thousands or millions of technological civilizations. Time deepens the paradox further. Our universe has existed for 13.8 billion years, while Earth is only about 4.5 billion years old. Our technological civilization is less than 200 years old, if we measure from the Industrial Revolution, or at most a few thousand years old. If we consider the emergence of early technologies like writing and metallurgy, this means there has been ample time for countless civilizations to emerge throughout the cosmos, potentially millions or billions of years before our own. Some of these civilizations could have had sufficient time to develop technologies far beyond our imagination, expand across their star systems, and perhaps even begin interstellar exploration and colonization. Yet when we look to the stars, we find only silence and apparent emptiness, with no clear signs of extraterrestrial intelligence. This silence is particularly puzzling given the potential for exponential expansion. If a civilization developed the technology for interstellar travel, even at relatively modest speeds of 10 to 20% the speed of light, they could potentially colonize an entire galaxy within a few million years, a mere eye blink in cosmic time. American physicist and mathematician John von Neumann theorized self-replicating spacecraft that could build copies of themselves using raw materials harvested from asteroids and other celestial bodies. Such von Neumann probes would enable an even faster spread across the galaxy, with each new outpost spawning additional probes to continue the expansion. Yet we see no evidence of such galactic engineering or colonization efforts, neither in our own solar system nor in observations of distant star systems where we might expect to detect the clear signatures of advanced technological activity. The so-called Drake equation, formulated by astronomer Frank Drake in 1961, attempts to quantify the number of active, communicative, extraterrestrial civilizations in our galaxy. The equation multiplies 7 factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, the fraction of those planets where life actually emerges, the fraction of life-bearing planets where intelligence evolves, the fraction of intelligent species that develop technology capable of interstellar communication, and the average longevity of such technological civilizations. Early estimates by Drake and others suggested there might be thousands or even millions of technological civilizations in our galaxy alone. Yet as we've improved our understanding of these factors over the decades, we found ourselves increasingly unable to explain the apparent absence of detectable alien intelligence. Numerous explanations have been proposed to resolve the Fermi Paradox. With varying degrees of plausibility and optimism, these potential solutions tend to focus on different terms in the Drake equation, challenging our assumptions about how common various developmental steps might be. Perhaps the most sobering explanation is the concept of the Great Filter, a term coined by economist Robin Hanson to describe a developmental hurdle so difficult that few, if any, civilizations manage to overcome it. This filter could exist somewhere in our past, meaning Earth-like life is extraordinarily rare, because some step in our evolutionary history, the emergence of complex cells, multicellular life, intelligence, or technology, is vanishingly improbable. Alternatively, and more worryingly, the Great Filter might lie in our future, suggesting that technological civilizations typically destroy themselves shortly after reaching our current stage of development, whether through nuclear war, engineered pandemics, artificial intelligence gone awry, or environmental collapse. Another class of explanations suggests that advanced civilizations might exist but remain undetectable to us. Perhaps the transition from biological to technological life happens rapidly, with advanced civilizations abandoning physical existence for virtual reality or some form of post-biological consciousness. Such civilizations might have little interest in cosmic expansion or might operate at energy levels or through communication channels we cannot yet detect. Some theorists propose that truly advanced civilizations would naturally evolve toward extreme efficiency, minimizing their waste heat and electromagnetic emissions, potentially becoming virtually invisible to our current observational methods. Others suggest that extraterrestrial intelligence might deliberately hide itself from detection, perhaps viewing emerging civilizations like ours as unpredictable or dangerous, following some sort of cosmic non-interference directive, or simply considering the vast majority of the universe uninteresting compared to the rich experiences available through advanced virtual or post-biological existence. The concept of self-imposed isolation has given rise to the zoo hypothesis, proposed by MIT radio astronomer John Ball. This explanation suggests that advanced civilizations have collectively agreed to quarantine developing planets like Earth, allowing them to evolve naturally without outside interference. We might be living in what amounts to a cosmic wildlife preserve, carefully observed but never contacted. A related idea is the planetarium hypothesis, which suggests we might be deliberately shown a false version of the universe, an incredibly sophisticated simulation or illusion created by advanced civilizations to hide their existence while they study our development. While these scenarios might sound far-fetched, they highlight an important point. Truly advanced civilizations might have motivations and capabilities so foreign to our understanding that their absence of communication with us could be entirely deliberate and calculated. Alternatively, the paradox might be resolved through the sheer vastness of space and time. Even if thousands of technological civilizations have existed throughout our galaxy's history, they might be so widely separated in space and time that meaningful contact is extraordinarily rare. The rare Earth hypothesis, articulated by paleontologist Peter Ward and astronomer Donald Brownlee, suggests that while simple microbial life might be common throughout the universe, the specific conditions required for complex multicellular life are exceedingly rare. Earth's large moon stabilizing our axial tilt, our position in a Goldilocks zone, not too close to the galactic center but not too far in the outskirts, our protective gas giant Jupiter deflecting potentially catastrophic impacts, and our planet's fortuitous combination of plate tectonics, liquid water, and stable atmosphere might represent an extraordinarily uncommon planetary configuration. If Earth truly is an exceptional rarity, it would explain why we haven't detected other civilizations. They simply don't exist in numbers large enough to make detection likely. Communication limitations offer another potential explanation. Our civilization has been broadcasting radio signals for only about a century, a cosmic eye blink, and these signals quickly become indistinguishable from background noise at interstellar distances unless deliberately focused and amplified. Advanced civilizations might use communication technologies far more sophisticated than radio, perhaps quantum entanglement, neutrinos, gravitational waves, or something we haven't yet conceived. They might also communicate at timescales either much faster or much slower than what we consider normal, making their transmissions appear as either meaningless noise or unchanging background to our detection systems. The vast majority of stars in our galaxy lie thousands of light years away, meaning even if we detected signals from a civilization at such distances, we would be receiving transmissions from their distant past, possibly long after they had gone extinct or evolved beyond recognition. The longevity of technological civilizations represents a crucial factor in the Fermi equation and might provide the most sobering explanation for the paradox. Perhaps technological intelligence inevitably creates the means of its own destruction and rarely survives more than a few centuries beyond developing advanced technology. Nuclear weapons, artificial intelligence, biotechnology, nanotechnology, and environmental degradation all represent potential existential threats that technological civilizations must navigate. If most fail this test and collapse or destroy themselves, the galaxy might be filled with the ruins of once promising civilizations that flickered briefly before extinguishing themselves. The alternative, that some technological civilizations do achieve long-term stability and continued advancement, raises the question of why such enduring civilizations haven't spread throughout the galaxy or made themselves known to emerging intelligences like ourselves. An intriguing recent addition to Fermi Paradox discussions is the dark forest theory, popularized by Chinese science fiction author Liu Cixin in his novel The Three-Body Problem. This hypothesis suggests that all intelligent life instinctively understands that other technological civilizations represent potential existential threats. Given the vast distances between stars, meaningful communication and trust building would be nearly impossible. leading to a situation where civilizations remain silent and hidden to avoid attracting attention. Like hunters in a dark forest who know others are present but cannot see them, the safest strategy is to remain concealed. This explanation suggests the cosmos might indeed be filled with technological civilizations, all deliberately maintaining radio silence and minimizing their detectable footprint out of self-preservation, creating a universe that appears empty despite being populated with wary, hidden intelligences. Timing might also explain the paradox. Perhaps we are simply among the first technological civilizations to emerge in our galaxy. While this might seem improbable given the age of the universe, several factors could explain such cosmic earliness. The universe needed time to produce the heavy elements necessary for rocky planets and complex life through multiple generations of stars. Additionally, complex life on Earth took nearly 4 billion years to evolve from the first simple cells, suggesting that the transition from microbial to complex multicellular life might be an extraordinarily difficult evolutionary leap. If intelligent technological life typically requires something close to the full duration that Earth-like planets have been possible in the universe, then we might indeed be among the first wave of such civilizations. In this scenario, the galaxy isn't empty. It's just beginning to awaken, with humanity among the cosmic early risers who will eventually be joined by other emerging intelligences. Our search for extraterrestrial intelligence, SETI, has been remarkably limited given the scale of the question. Traditional radio SETI has examined only a tiny fraction of the radio spectrum, focused on a few thousand nearby stars at most. Optical SETI, looking for laser signals, has been even more limited in scope. We've sent only 5 spacecraft beyond our solar system, the Pioneer and Voyager probes, and they have barely crossed into interstellar space. Our most powerful telescopes are only now gaining the ability to study the atmospheres of exoplanets for potential biosignatures. Given these limitations, perhaps we simply haven't looked thoroughly enough to find the evidence that does exist. As astronomer Jill Tarter, one of SETI's pioneers, has pointed out, claiming the universe is empty based on current search efforts would be like concluding there are no fish in Earth's oceans after examining a single glass of seawater. New approaches to the search for extraterrestrial intelligence are expanding beyond traditional radio astronomy. Researchers are now looking for technosignatures, observable evidence of technologies that might be created by advanced civilizations. These include searching for the waste heat of massive energy harvesting structures like Dyson spheres, hypothetical megastructures that would partially or completely encompass a star to capture its energy output, artificial light or atmospheric pollutants on exoplanets, or unusual stellar light curves that might indicate massive orbital construction projects. Astronomers are also developing methods to detect the signs of interstellar spacecraft propulsion systems or industrial-scale activities around other stars. These broader search parameters acknowledge that advanced civilizations might not be actively trying to communicate with us, but could still leave detectable traces of their technological activities. The search for biosignatures, chemical evidence of life, on exoplanets represents another promising approach that might help resolve the paradox. The James Webb Space Telescope and other next-generation observatories can analyze the atmospheres of planets orbiting nearby stars, looking for combinations of gases that would be difficult to explain through non-biological processes. The detection of oxygen, methane, and water vapor together, for instance, would strongly suggest the presence of life, as these gases would normally react with each other and disappear without continuous biological replenishment. While such discoveries wouldn't necessarily indicate technological civilizations, finding that life has independently evolved on multiple worlds would suggest that the emergence of life itself is not a great filter. This would narrow the range of explanations for the Fermi Paradox, potentially indicating that the transition from simple life to intelligence and technology represents the most difficult evolutionary leap. The implications of resolving the Fermi Paradox, in whatever direction, would profoundly reshape humanity's understanding of our cosmic significance. If we ultimately discover that technological civilizations are common throughout the universe, It would trigger perhaps the greatest cultural and philosophical revolution in human history. Contact with other intelligences would provide unprecedented opportunities for learning and exchange, while also forcing us to confront beings potentially far more advanced than ourselves. Conversely, if we progressively eliminate potential explanations and conclude that technological civilizations are indeed extraordinarily rare or non-existent beyond Earth, it would place an immense responsibility on humanity as potentially the only or one of very few intelligent stewards of cosmic consciousness. Either resolution would transform our species' self-understanding and our sense of purpose in the universe. Perhaps the most important insight from the Fermi Paradox is how it highlights humanity's profound cosmic ignorance. We are attempting to understand the prevalence of technological intelligence throughout the cosmos based on a sample size of exactly one, ourselves. We have no way of knowing whether Earth's evolutionary history is typical or highly unusual, whether our form of carbon-based intelligence is the most common or merely one of countless possibilities, or whether our technological development follows patterns typical of intelligent species. We make assumptions based on what we would do: build radio transmitters, expand across our solar system, send probes to nearby stars, without knowing whether these behaviors represent universal tendencies of intelligent life or merely the peculiar preoccupations of one young technological species on a single small planet, orbiting an ordinary star in the outskirts of an average galaxy. As we peer into the cosmic silence, we must also consider that our search assumptions might be fundamentally limited by our human perspective. We tend to look for civilizations following development patterns similar to our own, using radio communication, expanding physically across space, harnessing progressively greater energy sources. But truly advanced intelligence might follow entirely different trajectories. Perhaps the natural evolution of technological civilization leads inward rather than outward, toward the exploration of inner space through consciousness, manipulation, virtual realities, or the engineering of subjective experience. Maybe advanced civilizations discover physics we don't yet comprehend, allowing them to slip away into parallel dimensions or create pocket universes. Or perhaps they transcend the duality between mind and matter entirely, evolving into forms of consciousness so different from our own that we lack the conceptual framework to imagine them, let alone detect their presence in the cosmos. The most profound resolution to the Fermi Paradox might be that we are simply asking the wrong questions. Our assumptions about what constitutes intelligence, civilization, technology, and communication might be parochial and limited. When Europeans first encountered gorillas, these intelligent primates had existed alongside humans for millions of years without developing writing, metallurgy, or other technologies we associate with civilization. Yet gorillas are perfectly adapted to their ecological niche, with complex social structures and forms of communication suited to their needs. Perhaps what we consider the inevitable march of progress, from stone tools to space travel, represents just one possible pathway that intelligent life might follow, with countless others we cannot yet imagine. The universe might be filled with intelligences that have taken entirely different evolutionary paths, creating forms of civilization so unlike our own that they remain invisible to us not through deliberate concealment but through fundamental differences in what it means to be an advanced form of life. The Fermi Paradox represents not just a scientific question, but a mirror reflecting humanity's deepest hopes and fears about our place in the cosmos. The possibility that we are alone, or nearly alone, carries both the terror of cosmic solitude and the exhilaration of unique cosmic significance. The alternative, that the universe teems with intelligences we have yet to detect, simultaneously offers the promise of cosmic community and the potential threat of competition or irrelevance. How we approach the search for extraterrestrial intelligence, what evidence we prioritize, and what explanations we find most compelling often reveal as much about human psychology and culture as they do about the objective reality of life in the universe. Perhaps this is why the Fermi Paradox has maintained such enduring fascination. It asks not just whether aliens exist, but what it means to be human in a universe that might or might not contain others like ourselves. As we continue exploring our solar system, deploying more powerful telescopes, and developing new search techniques, we can expect the constraints on possible solutions to the Fermi Paradox to gradually tighten. Each exoplanet atmosphere we analyze, each new star system we examine for technosignatures, each experiment in astrobiology narrows the range of possibilities. Perhaps within decades or centuries, evidence will emerge that decisively resolves the paradox one way or another. Until then, the apparent emptiness of our cosmic neighborhood remains both a profound puzzle and an invitation to expand our imagination beyond the limits of our current understanding. The quest to answer Fermi's simple question, "Where is everybody?" drives us to explore not just outer space, but the boundaries of what we consider possible for life, intelligence, and civilization throughout the vast and ancient cosmos. Having examined the profound questions raised by the Fermi Paradox, we now turn to another fundamental mystery, one that shapes all others, yet remains perhaps the least understood aspect of our reality. Time, the dimension through which all change occurs, represents science's most elusive concept. While we experience time as the universal flow from past to future, modern physics suggests a far stranger reality, one where time's apparent simplicity masks profound complexities that challenge our most basic intuitions about reality itself. In our next section, we'll explore the true nature of time, how it bends, stretches, and perhaps even emerges from deeper quantum phenomena, and whether what we perceive as time's arrow might be more illusion than fundamental truth about our universe. Time is perhaps the most fundamental aspect of our experience, the medium through which all events unfold, the rhythm that governs our lives from heartbeat to heartbeat, sunrise to sunset, birth to death. We structure our existence around it, measure it with exquisite precision, and organize our societies according to its passage. Yet despite our intimate familiarity with time, it remains one of science's most profound mysteries. Is time a fundamental property of the universe, flowing inexorably forward as we perceive it? Or is it something else entirely, perhaps an emergent property arising from deeper quantum processes, or even an illusion created by our consciousness to make sense of a reality fundamentally different from our perception? As we explore the frontiers of physics, from the quantum realm to the cosmic scale, our understanding of time has been repeatedly challenged, revealing a concept far stranger and more elusive than our everyday experience suggests. Our intuitive understanding of time seems self-evident. It flows uniformly and universally forward, carrying all existence from past to future in a steady, unstoppable current. We divide it into regular units, seconds, days, years, assuming these measurements reflect an objective reality. Yet this common-sense view of time began to fracture in 1905, when Albert Einstein published his special theory of relativity. Einstein demonstrated that time is not absolute but relative, flowing at different rates depending on the observer's velocity. Two identical clocks will tick at different rates if one is moving relative to the other, a phenomenon called time dilation that has been confirmed with extraordinary precision using atomic clocks on airplanes and GPS satellites. At speeds approaching the speed of light, these effects become dramatic. A theoretical astronaut traveling at 99% the speed of light would experience only 1 year, while 14 years passed on Earth, returning to find children grown and friends aged, while they themselves remained relatively young. General relativity, Einstein's theory of gravity published a decade later, revealed even more profound distortions of time. According to this framework, gravity itself warps time. The stronger the gravitational field, the slower time passes. A clock at sea level runs measurably slower than one on a mountaintop, not because of any mechanical difference, but because time itself flows differently in these locations due to their distance from Earth's gravitational center. This effect becomes extreme near massive objects like black holes, where time can slow to a near standstill relative to distant observers. These aren't mere theoretical curiosities. but demonstrable physical realities that engineers must account for when designing GPS systems and that astronomers observe when studying light from compact stellar remnants. The uniform, universal time of our intuition has given way to a flexible space-time fabric that curves, stretches, and contracts in response to mass and energy. One of the most profound consequences of relativity is the realization that simultaneity itself is relative. Events that appear to happen at the same time to one observer may occur at different times for another observer in motion. This shatters the notion of a universal now spanning the cosmos. When we gaze at distant galaxies, we don't see them as they are now, whatever that might mean, but as they were when light left them millions or billions of years ago. The fabric of reality does not have a special, universal present moment slicing across it. Instead, different observers moving relative to each other will disagree about which events are simultaneous, with neither perspective being more correct than the other. This doesn't merely complicate our understanding of time, it fundamentally transforms it, replacing the flowing river of classical time with a four-dimensional structure where past, present, and future all exist together in what physicists call the block universe. The block universe view, embraced by many physicists, suggests that time doesn't flow, but rather that all moments, past, present, and future, exist simultaneously in a four-dimensional structure. From this perspective, our subjective experience of the present moment moving from past to future is an illusion. As Einstein himself wrote in a letter consoling the family of his deceased friend, Michel Besso, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion." In this view, the universe is more like a complete existing film reel than a movie actively unfolding. Our consciousness creates the illusion of the present moment moving through this reality, but the entire timeline, from the Big Bang to the far future, exists as a complete structure. While philosophically challenging, this perspective elegantly explains many features of relativity and aligns with the mathematical formulation of space-time as a unified four-dimensional manifold. Yet quantum mechanics, our other pillar of fundamental physics, presents a seemingly contradictory view of time. In quantum theory, time appears as an external parameter rather than a dynamical variable. It's the background against which quantum states evolve, rather than something that itself evolves. The infamous measurement problem in quantum mechanics introduces a strange temporal asymmetry. Before measurement, quantum systems exist in superpositions of multiple states, while after measurement, they collapse to definite values. This process appears irreversible and time-directional in a way that seems at odds with the time-symmetric equations of both quantum mechanics and relativity. Some interpretations of quantum mechanics, like Hugh Everett's many worlds interpretation, attempt to preserve time symmetry by suggesting that all possible outcomes of quantum measurements occur in branching parallel universes. But this creates as many philosophical problems as it solves. The tension between quantum mechanics and general relativity becomes most acute when considering black holes, where extreme gravity creates conditions requiring both theories to describe reality. Stephen Hawking's groundbreaking work on black hole thermodynamics revealed that black holes slowly evaporate over time through quantum effects, eventually disappearing completely. This process appears irreversible. Information about what fell into the black hole seems permanently lost, violating the quantum mechanical principle that information cannot be destroyed. This black hole information paradox remains one of the greatest unsolved problems in theoretical physics and highlights our incomplete understanding of how time operates in extreme conditions where quantum effects and gravity both dominate. Various proposed resolutions, including the holographic principle, which suggests information is preserved on the black hole's event horizon, remain active areas of research, but have yet to provide a fully satisfactory resolution to this fundamental temporal puzzle. While physicists grapple with time at nature's extremes, a more immediate question confronts us. Why does time appear to flow in only one direction? The fundamental laws of physics, from Newton's mechanics to Einstein's relativity to quantum field theory, are almost entirely time-symmetric, working equally well whether time runs forward or backward. Yet we experience a profound temporal asymmetry. Eggs break but never spontaneously reassemble. Coffee cools but never spontaneously heats up. People age but never grow younger. This arrow of time represents one of physics' greatest unsolved problems. The most widely accepted explanation ties this asymmetry to entropy, the measure of disorder in a system. According to the second law of thermodynamics, the total entropy of a closed system always increases over time. This provides a direction to time's flow from lower to higher entropy states, but doesn't explain why the universe began in a low entropy state to begin with, a condition that physicist Roger Penrose has called ridiculously improbable, and that may require explanation through cosmological processes we don't yet understand. Multiple arrows of time exist in nature, all apparently pointing in the same direction. The thermodynamic arrow involves entropy increase. The psychological arrow reflects our ability to remember the past but not the future. The cosmological arrow points from the Big Bang toward the universe's expansion. The radiative arrow describes how electromagnetic waves expand outward from sources rather than converging inward. While these arrows align in our universe, physicists debate whether this alignment is necessary or contingent. Some theoretical work suggests that in certain conditions, perhaps in a hypothetical universe undergoing contraction rather than expansion, some of these arrows might point in opposite directions, creating regions where time effectively runs backward from our perspective. Such speculation remains highly theoretical, but it highlights how little we truly understand about time's fundamental nature and direction. Beyond these physical considerations lies an even deeper mystery: the relationship between time and consciousness. Our subjective experience of time, the feeling of being in the present moment, with memories of the past and anticipations of the future, might be more than just a passive registration of external temporal reality. Some philosophers and scientists suggest that consciousness actively constructs our experience of time, creating the sensation of flow and the sharp distinction between past, present, and future that physics increasingly suggests may be illusory. Neuroscience reveals that our brains process different sensory inputs at varying speeds and must actively synchronize them to create a coherent experience of now. This synchronization involves small delays and predictive processing, suggesting that our experience of the present moment is actually a carefully constructed model rather than direct perception of temporal reality. Whether consciousness creates time or merely perceives an independently existing temporal dimension remains one of the most profound, interdisciplinary questions spanning physics, neuroscience, and philosophy. Time's apparent flow creates another puzzle. Can time itself have a beginning or end? The Big Bang theory suggests our universe began approximately 13.8 billion years ago, but whether this represents the beginning of time itself remains debated. Some models, like the no-boundary proposal developed by Stephen Hawking and James Hartle, suggest that asking about time before the Big Bang is meaningless, like asking about locations north of the North Pole. In this view, time emerged as part of space-time with the universe's birth, with the very concept of before losing meaning at the Big Bang. Alternatively, various cyclic universe models propose that our Big Bang might be one in an eternal series of expansions and contractions, with time extending infinitely into the past and future. The question of time's possible end is equally speculative, whether in a big freeze as the universe expands forever, a big crunch of eventual collapse, or a big rip where dark energy tears apart the fabric of space-time itself. These possibilities remind us that time itself may be contingent, a feature of our particular universe, rather than a necessity of existence. The relationship between time and causality presents another fundamental puzzle. We intuitively understand causality as requiring temporal order, causes must precede their effects. Yet some interpretations of quantum mechanics challenge this assumption. The delayed choice quantum eraser experiment, for instance, seems to suggest that measurements made in the present can influence how we must describe events in the past. While these experiments don't allow information to travel backward in time, preventing genuine paradoxes, they do challenge our intuitive notion that the past is fixed and immutable. Similarly, certain solutions to Einstein's equations of general relativity theoretically permit closed time-like curves, paths through spacetime that return to their starting point in both location and time, effectively allowing for time travel. While no evidence suggests such paths exist in our universe, their theoretical possibility in our best physical theories indicates how poorly we understand time's true nature and limitations. The quest to unify quantum mechanics and general relativity, the holy grail of modern theoretical physics, has profound implications for our understanding of time. Various approaches to quantum gravity, including string theory and loop quantum gravity, suggest that at the most fundamental level, space-time might not be continuous, but discrete, composed of minimal units at the incredibly tiny Planck scale. Some theories go further, suggesting that space and time aren't fundamental at all, but emerge from deeper quantum structures. Loop quantum gravity, for instance, describes space-time as a network of interwoven loops, while certain formulations of string theory suggest space-time emerges from the collective behavior of more fundamental quantum entities. If these approaches prove correct, time as we understand it may be merely an approximation, a large-scale emergent feature of reality rather than a fundamental aspect of existence. Physicist Carlo Rovelli's relational interpretation of quantum mechanics extends this idea, suggesting that time might be entirely relational rather than absolute. In this view, temporal evolution doesn't happen against the background of some external universal time, but emerges from interactions between physical systems. Different systems effectively create their own time through their interactions, with no overarching cosmic time coordinating everything. This perspective aligns with general relativity's demonstration that time flows differently depending on gravitational conditions and relative motion, but takes the idea further, suggesting that time itself might be an emergent property rather than a fundamental dimension. If correct, this would transform our understanding not just of physics, but of existence itself, suggesting that underneath our time-structured experience lies a more fundamental reality where time as we know it dissolves into a complex network of interactions with no universal flow or direction. Some of the strangest implications for time come from quantum entanglement, what Einstein famously called spooky action at a distance. When particles become entangled, measuring one instantly affects the state of the other, regardless of the distance separating them. This seemingly instantaneous connection across space raises profound questions about time, as it appears to involve faster-than-light influence. While deeper analysis shows that no usable information travels faster than light, preserving causality, entanglement still challenges our understanding of temporal order in quantum systems. Recent theoretical work on quantum non-locality in time suggests that quantum correlations might operate not just across space, but across time as well, potentially connecting past and future states in ways that defy classical causality. These investigations represent the cutting edge of quantum foundations research and may eventually lead to a radical reconceptualization of time's nature in quantum systems. The philosophical implications of modern physics' view of time are profound and unsettling. If time is not what it seems, if the flow we experience is illusory, if past and future already exist in a block universe, if fundamental reality may lack time altogether, what does this mean for human concepts like free will, creativity, and moral responsibility? These notions seem to require an open future not yet determined, yet physics increasingly suggests a picture where all of time exists at once. How do we reconcile our lived experience of making choices that shape an undetermined future with a physical reality where time may be complete and unchanging? Various philosophers have attempted to reconcile these perspectives, arguing that even in a block universe, the distinctions between past, present, and future remain meaningful from our perspective within the timeline, and that concepts like causality and choice can be reformulated to make sense within this framework. Others suggest that consciousness itself might play a role in resolving these tensions, perhaps through some yet undiscovered connection between mind and the quantum realm. Our practical mastery of time measurement stands in stark contrast to our theoretical confusion about its nature. Modern atomic clocks can measure time with staggering precision, losing less than 1 second over billions of years, allowing for technologies like GPS that depend on nanosecond timing accuracy. Yet, even as we perfect the measurement of time, we find ourselves increasingly uncertain about what exactly we're measuring. This paradox reflects a broader pattern in science, where our technological capabilities often outpace our conceptual understanding. We can manipulate phenomena with extraordinary precision without fully grasping their fundamental nature. Time may represent the ultimate example of this pattern, a dimension we navigate with increasing technological sophistication while remaining profoundly uncertain about its true character and origins. Time travel, a staple of science fiction, represents a natural extension of these fundamental questions about time's nature. While general relativity theoretically permits closed time-like curves that could allow journeys into the past, enormous practical obstacles exist. Creating such paths would require exotic forms of matter with negative energy density or cosmic structures like wormholes that might not exist in our universe. More fundamentally, time travel into the past raises logical paradoxes that may indicate its physical impossibility. The grandfather paradox, where a time traveler prevents their own birth by interfering with their ancestors, creates logical contradictions that some physicists argue would be resolved by making backward time travel impossible in the first place. Others propose that such paradoxes might be resolved through parallel timelines or self-consistent loops, where attempts to change the past actually contribute to creating the known history. Travel into the future, by contrast, faces no logical contradictions and is theoretically possible through time dilation. One could effectively jump forward in time by traveling at near light speeds or orbiting close to a black hole. As we contemplate time's mysteries, practical questions arise about its relationship to space exploration and communication. The vast distances between stars create what we might call temporal provincialism, the isolation of different regions of space-time due to light's finite speed. A message sent to even the nearest star system, Alpha Centauri, takes over 4 years to arrive, with the reply taking another 4. Communication with a potential civilization in the Andromeda Galaxy would involve message delays of over 2.5 million years, longer than human civilization has existed. This limitation means that no galactic community could ever share a meaningful present moment or engage in real-time conversation. Any interstellar civilization would need to function across vast temporal gulfs, perhaps developing entirely different concepts of communication, cooperation, and communal identity than those possible in our Earthbound experience, where instant communication has become the norm. In this sense, the nature of time may fundamentally constrain the forms of life and civilization possible on a cosmic scale. The future of time research lies at the intersection of multiple disciplines. Quantum gravity theories continue to explore time's fundamental nature at the smallest scales. Cosmology examines time's behavior in the early universe and its possible beginning and end. Quantum information theory investigates temporal aspects of entanglement and information processing. Neuroscience studies how the brain creates our subjective experience of time's passage. Computer science explores how information processing systems might experience or simulate temporality. This multidisciplinary approach recognizes that time may not be a single phenomenon with a single explanation, but rather a multi-layered concept with different aspects emerging at different scales and in different contexts. The convergence of these research programs might eventually produce a unified understanding of time that reconciles the mathematical time of physics, the experiential time of consciousness, and the cosmological time of universal evolution. Throughout history, our understanding of time has repeatedly transformed, from ancient cyclical conceptions to Newton's absolute time, to Einstein's relative space-time, to the quantum and emergent perspectives of cutting-edge physics. Each revolution hasn't merely refined our knowledge, but fundamentally altered what we believe time to be. This historical pattern suggests we should approach our current theories with humility, recognizing that future discoveries may transform our understanding just as profoundly. The nature of time may be the ultimate mystery precisely because it's not merely an object of study, but the medium through which all study occurs. Not just something we observe, but an integral part of the observational process itself. Perhaps complete understanding of time would require stepping outside time, a paradoxical and potentially impossible perspective that highlights the intrinsic limitations of our temporally bound consciousness when investigating the very ground of its own existence. As we conclude our exploration of time's mysteries and prepare to consider our final question, the limits of human knowledge itself, we might reflect on time's dual nature as both our most intimate companion and our most elusive quarry. We experience time directly, continuously, inescapably, yet struggle to define or explain it. St. Augustine's famous observation remains as relevant today as when he wrote it in the 4th century. What then is time? If no one asks me, I know what it is. If I wish to explain it to someone who asks, I do not know. This tension between intuitive experience and conceptual understanding gets to the heart of the scientific enterprise itself. Our attempt to translate direct experience into precise models and theories that can explain and predict the world around us. As we'll see in our next section, this fundamental project of translating experience into understanding faces inherent limitations that may permanently restrict what we can know about the universe, regardless of our technological advancement or intellectual evolution. As we approach the conclusion of our cosmic journey through the depths of the unknown universe, we confront perhaps the most fundamental question of all. Are there inherent limits to what humans can know? Throughout history, our species has made extraordinary progress in understanding the cosmos. From ancient astronomical observations to quantum field theory, from early classifications of living things to the mapping of the human genome. Yet despite these remarkable advances, certain boundaries to knowledge persistently appear on our intellectual horizon. Some of these boundaries may be temporary, practical limitations that future technological and theoretical innovations will eventually overcome. Others, however, may represent fundamental constraints inherent in the nature of reality itself, in the structure of our minds, or in the relationship between mind and reality. The most obvious limitations to knowledge are practical ones, barriers that exist not because understanding is impossible in principle, but because gathering the necessary evidence presents insurmountable challenges. Consider the cosmic horizon beyond which we cannot see. Regardless of technological advancement, light from beyond approximately 46 billion light-years, our current cosmic horizon, will never reach us due to the universe's accelerating expansion. This means entire regions of the cosmos are observationally inaccessible to us. Similarly, information that fell into black holes may be permanently lost, and events that occurred before the cosmic microwave background radiation was emitted remain largely obscured by the fog of the early universe. These horizon problems represent not failures of human ingenuity, but built-in limitations resulting from our specific position in space and time. Beyond these observational limitations lie the challenges of scale, both immense and minuscule. At extremely small scales, Heisenberg's uncertainty principle places fundamental limits on our ability to simultaneously measure complementary properties like position and momentum. This isn't merely a technological limitation, but a feature of quantum reality itself. At the Planck scale, our current theories of physics break down entirely. Meanwhile, at cosmic scales, dark energy and dark matter, which together constitute approximately 95% of the universe's total mass energy, remain mysterious despite decades of investigation. These scale limitations force us to rely increasingly on mathematical models and indirect evidence rather than direct observation, introducing additional layers of uncertainty between us and the phenomena we seek to understand. The complexity barrier represents another profound challenge to complete knowledge. Many systems in nature, from weather patterns to ecosystems to human brains, display emergent properties and chaotic behaviors that make precise predictions fundamentally impossible, even with perfect knowledge of initial conditions. Chaos theory demonstrates that in non-linear systems, infinitesimal differences in starting conditions can lead to vastly different outcomes over time, the famous butterfly effect. This sensitivity to initial conditions means that even if we had perfect mathematical models of complex systems, our ability to predict their behavior would still be fundamentally limited by the precision with which we can measure their current state. Some systems are so complex that they may be computationally irreducible, meaning there's no way to predict their future states except by simulating their evolution step by step, with no shortcuts possible. The limitations of mathematics itself present surprising constraints on knowledge. Kurt Gödel's incompleteness theorems demonstrated that in any formal mathematical system complex enough to include basic arithmetic, there will always be true statements that cannot be proven within that system. This profound result shattered the hope that mathematics could provide a complete, consistent foundation for all knowledge. Later, Alan Turing proved the halting problem unsolvable, showing that no algorithm can determine whether an arbitrary computer program will eventually halt or run forever. These results suggest that even in the precise realm of mathematics and computation, certain forms of complete knowledge are provably unattainable. Since physics relies heavily on mathematics to describe reality, these mathematical limitations may translate into fundamental limitations on our ability to fully describe physical systems. Biological constraints on human cognition may impose additional limits on what we can know. Our brains evolved to navigate the mesoscale world of predators, prey, and social relationships, not to intuitively understand quantum mechanics or hyperdimensional spaces. When physicists describe quantum superpositions or extra dimensions curled up at microscopic scales, they use mathematics that works predictively but defies intuitive visualization, as Richard Feynman famously noted about quantum mechanics. I think I can safely say that nobody understands quantum mechanics. Even experts who can manipulate the equations flawlessly struggle to form intuitive mental models of what those equations actually describe. These cognitive limitations raise a profound question. Are there aspects of reality that can be described mathematically but never truly comprehended by human minds? The quantum measurement problem presents perhaps the most profound example of how observation itself may fundamentally limit knowledge. According to standard interpretations of quantum mechanics, the act of measurement causes a quantum system to collapse from multiple superposed potential states into a single definite state. This suggests that reality at the quantum level isn't fully deterministic in the classical sense. We can calculate probabilities for different outcomes, but cannot predict with certainty which particular outcome will occur in a single measurement. Moreover, certain properties of quantum systems cannot be simultaneously determined beyond specific uncertainty limits, regardless of measurement precision. These features suggest that indeterminism and uncertainty may be fundamental features of reality at the smallest scales, not merely limitations of our measuring instruments or techniques. The hard problem of consciousness, why and how physical processes in the brain give rise to subjective experience, has resisted scientific explanation despite significant advances in neuroscience. The subjective, first-person nature of consciousness seems fundamentally different from the objective, third-person perspective of physical science. This creates what philosopher Joseph Levine called an explanatory gap between physical descriptions of brain activity and the felt experience of being conscious. Some philosophers argue that consciousness represents a fundamentally different kind of phenomenon from physical processes, perhaps a basic feature of reality not reducible to physics and chemistry. If true, this would suggest that a complete physical theory of the universe would still leave something essential unexplained. The persistent challenge of connecting subjective experience to objective physical processes may indicate a fundamental limitation in our ability to develop a unified theory encompassing both the physical world and conscious experience. The possibility of multiple valid perspectives presents another challenge to the ideal of complete knowledge. Different scientific disciplines study the same phenomena at different levels of organization using different conceptual frameworks, from particle physics to chemistry to biology to psychology to sociology. Each level captures real patterns that might be missed at other levels. These complementary perspectives raise questions about reductionism, the view that higher-level phenomena can ultimately be fully explained in terms of lower-level processes. While reduction has proven powerful in many contexts, complex systems often display emergent properties that, while compatible with lower-level explanations, cannot be predicted from them alone. This suggests that complete knowledge might require not just a single unified theory, but multiple complementary frameworks, each capturing different aspects of a multifaceted reality. Some potential limits to knowledge arise from the possibility that aspects of reality might be fundamentally causal or random. While classical physics presented a deterministic universe where perfect knowledge of initial conditions would allow perfect prediction of future states, quantum mechanics introduced elements of fundamental randomness. In the standard Copenhagen interpretation, the specific outcome of a quantum measurement cannot be predetermined. Even in principle, only the probabilities of different outcomes can be calculated. If such randomness is truly fundamental, rather than merely reflecting hidden variables we haven't yet discovered, then certain events may have no cause beyond probabilistic quantum fluctuations. This would place absolute limits on predictive knowledge, not because of practical limitations in measurement precision, but because some events simply have no prior causes that could be known. The finitude of human existence imposes practical constraints on knowledge acquisition. Individual human lifespans limit how much any person can learn, while the finite duration of human civilization constrains our collective knowledge accumulation. If humanity exists for only a few million years, already an optimistic estimate by evolutionary standards, vast cosmic processes occurring over billions or trillions of years will remain largely unobserved. Similarly, rare cosmic events that occur once per billion years might never be directly witnessed during humanity's existence. While we can partly overcome individual limitations through institutions that accumulate and transmit knowledge across generations, civilization itself has an unknown but finite lifespan. This temporal finitude means that even if there are no in-principle barriers to complete knowledge, the practical limitations of time ensure that human knowledge will always remain incomplete. The potentially infinite complexity of reality itself represents perhaps the ultimate challenge to complete knowledge. If reality is infinitely detailed, if there is no fundamental bottom level where explanation stops, then complete knowledge would be impossible even in principle. Every answered question would generate new questions about the mechanisms behind the answer in an infinite regress. The history of science shows a pattern of discovering ever deeper layers of structure, from visible objects to molecules to atoms to subatomic particles to quarks and beyond. If this pattern continues indefinitely, with each new layer revealing new complexities requiring new theoretical frameworks, then knowledge acquisition becomes an endless journey rather than a destination that could ever be fully reached. Complete knowledge would require infinite information processing capacity and infinite time, neither of which are available to finite beings like ourselves. Despite these various limitations, the history of scientific discovery gives grounds for optimism about expanding the boundaries of knowledge. Many phenomena once considered permanently mysterious have yielded to scientific investigation. Theoretical frameworks once considered the absolute pinnacle of understanding have been superseded by more comprehensive theories. Instruments have extended our senses far beyond their natural limits, from microscopes revealing the cellular basis of life to telescopes capturing light from the early universe. Computing technology has enabled us to process and analyze datasets of previously unimaginable complexity. These historical patterns suggest that at least some apparent limitations to knowledge reflect temporary constraints rather than permanent boundaries. The progressive expansion of human understanding, while never complete, has repeatedly transcended barriers that once seemed insurmountable. The recognition of these various limitations need to not lead to pessimism about human knowledge. Rather, it can foster epistemic humility, an awareness that our understanding, while powerful and expanding, remains inherently partial and situated. Throughout history, each era has believed itself close to complete understanding, only to discover new depths of complexity and new domains of inquiry. This pattern suggests that our current knowledge, impressive as it is, likely represents a tiny fraction of what might eventually be known, and an even tinier fraction of all that exists to be known. Rather than seeing this as a defeat, we might view it as an invitation to perpetual discovery, a recognition that the universe will always contain more mysteries than certainties, more questions than answers. Perhaps the greatest wisdom lies not in achieving complete knowledge, but in maintaining the balance between confidence in what we know and humility about how much remains unknown. As we conclude our exploration of cosmic mysteries, from dark matter to the multiverse, from black holes to the nature of time itself, we find ourselves confronting the most profound mystery of all, the inherent limitations of human understanding. Yet rather than diminishing our cosmic journey, these limitations give it meaning and poignancy. We are finite beings striving to comprehend an apparently infinite reality, a quest that can never be completed, but that has already yielded insights of extraordinary power and beauty. The universe may never be fully known, but it can be endlessly explored, each discovery revealing new horizons of ignorance and opportunity. In this ongoing dance between knowing and not knowing, between discovery and mystery, we find not frustration, but the endless adventure that gives scientific inquiry its deepest meaning and most profound joy. In our final section, we'll turn from these philosophical reflections on the limits of knowledge to the more concrete question of what comes next, the future of space exploration and discovery. As humanity stands on the threshold of potentially becoming a multi-planetary species, with new observatories peering deeper into space than ever before, and artificial intelligence accelerating the pace of scientific discovery, what new wonders and revelations await in the coming decades and centuries? How might future generations transform our understanding of the cosmos, even as they confront the same fundamental limitations we've explored in this section? As we stand at the threshold of a new era in our cosmic journey, the future of space exploration unfolds before us with unprecedented possibilities. Throughout human history, our relationship with the cosmos has evolved from naked-eye observations of wandering planets to rovers exploring the Martian surface and telescopes peering back to the dawn of time itself. Yet in many ways, we are still in the earliest chapters of humanity's cosmic story. The coming decades and centuries promise revolutions in our understanding of the universe and potentially in humanity's place within it. New telescopes, spacecraft, propulsion systems, and computing technologies are poised to transform our relationship with the cosmos, perhaps enabling us to answer some of the profound questions we've explored throughout this series. While the inherent limitations of knowledge we discussed previously will always constrain complete understanding, the frontiers of discovery continue to expand in ways our ancestors could scarcely have imagined. The most immediate transformation in our cosmic perspective will come from a new generation of observatories that dramatically extend our vision across the electromagnetic spectrum. The James Webb Space Telescope, with its 6.5-meter primary mirror and instruments optimized for infrared observation, represents the most powerful space observatory ever deployed. Operating at the L2 Lagrange point, 1.5 million kilometers from Earth, Webb's ability to peer through cosmic dust and detect the faintest infrared signatures will reveal unprecedented details about the earliest galaxies, the formation of stars and planetary systems, and the atmospheres of exoplanets. Webb's specialized instruments can analyze the light from multiple objects simultaneously across various infrared wavelengths, ideal for studying dust-enshrouded star-forming regions and protoplanetary disks. These capabilities will allow astronomers to observe galaxies formed just 200 million years after the Big Bang, study the atmospheric composition of potentially habitable exoplanets, and perhaps detect the first biosignatures, chemical markers of life, on worlds beyond our solar system. Meanwhile, ground-based behemoths like the extremely large telescope in Chile, with its astonishing 39-meter primary mirror composed of 798 hexagonal segments, will achieve resolution 15 times sharper than the Hubble Space Telescope. Using adaptive optics that correct for atmospheric distortion in real time, the ELT will potentially enable direct imaging of Earth-sized exoplanets, resolving structures as small as 25 light-years across in galaxies millions of light-years away. Other massive telescopes under construction include the 30-meter telescope and the giant Magellan telescope. Together, these observatories will collect billions of times more light than the human eye, revealing details about distant worlds, star formation, and galactic evolution that remain hidden even to current telescopes. Their spectrographs will analyze starlight passing through exoplanet atmospheres with unprecedented precision, potentially identifying thousands of potentially habitable worlds and characterizing their environments in detail. Across other wavelengths, facilities like the Square Kilometre Array and the next generation Very Large Array will revolutionize radio astronomy. The SKA, spanning facilities across South Africa and Australia to create a virtual telescope with a collecting area of 1 square kilometre, will generate data at rates exceeding the current global internet traffic. This unprecedented sensitivity will enable the detection of extremely faint radio signals, potentially including those from the cosmic dark ages before the first stars formed. By mapping the three-dimensional distribution of hydrogen throughout cosmic history, the SKA will trace the evolution of cosmic structure with unprecedented detail, potentially revolutionizing our understanding of dark matter and dark energy. Its ability to detect faint radio emissions from potentially habitable exoplanets might reveal technological signatures from extraterrestrial civilizations, if they exist and use radio technology, as part of the most comprehensive search for extraterrestrial intelligence ever conducted. Gravitational wave astronomy, barely a decade old, stands poised for dramatic advances that will transform our understanding of the universe's most extreme phenomena. While current facilities like LIGO and Virgo have already revolutionized astronomy by detecting merging black holes and neutron stars, their sensitivity remains limited to relatively nearby events and higher frequency gravitational waves. The space-based LISA, Laser Interferometer Space Antenna mission, will detect gravitational waves at much lower frequencies than ground-based instruments, using 3 spacecraft flying in formation separated by 2.5 million kilometers. This configuration will allow LISA to observe entirely different classes of sources, including the inspirals of supermassive black holes throughout cosmic history, ultra-compact binary systems within our own galaxy, and potentially primordial gravitational waves from shortly after the Big Bang. Meanwhile, third-generation ground-based detectors like the Einstein Telescope and Cosmic Explorer will increase sensitivity tenfold compared to current facilities, potentially detecting every black hole merger in the observable universe. These advanced gravitational wave observatories will transform cosmology by providing entirely new measurements independent of the traditional cosmic distance ladder. By detecting standard sirens, gravitational wave sources whose distances can be directly determined from the signal properties, astronomers can measure the expansion rate of the universe with unprecedented precision, potentially resolving tensions in current measurements of the Hubble constant. Perhaps most excitingly, gravitational wave detectors might discover entirely new classes of objects, exotic compact objects like boson stars, primordial black holes from the early universe, or even cosmic strings and domain walls predicted by some theoretical models. The coincident detection of neutrinos, gravitational waves and electromagnetic radiation from cataclysmic events will fully realize the promise of multi-messenger astronomy, providing complementary information about some of the universe's most energetic phenomena. The exploration of our own solar system will accelerate through a combination of robotic missions and potentially human presence beyond Earth orbit. NASA's Artemis program aims to return humans to the Moon by the mid-2020s, this time establishing a sustainable presence rather than flags and footprints missions. Initial landings near the lunar South Pole will allow explorers to investigate regions where water ice has been detected in permanently shadowed craters, a crucial resource for potential long-term habitation. The Lunar Gateway, a space station in lunar orbit, will serve as a staging point for surface missions and deep space exploration, incorporating international contributions from multiple space agencies. Unlike the Apollo program's brief visits, Artemis envisions establishing surface infrastructure for longer stays, potentially including habitats, power systems utilizing solar arrays positioned on crater rims with near-constant sunlight and scientific instruments for lunar geology, astronomy, and biology. These lunar operations could serve as proving grounds for technologies needed for eventual human missions to Mars, which multiple organizations, both governmental and private, have targeted for the 2030s or 40s. The red planet presents enormous challenges, from cosmic radiation exposure during the minimum 6-month journey, to the psychological effects of isolation, to the practical difficulties of landing and sustaining human life in such a harsh environment. Yet the scientific returns of human exploration could be immense, particularly in the search for evidence of past or present microbial life on Mars. Humans can perform complex, adaptive scientific investigations far beyond the capabilities of current robotic explorers, drilling deeper beneath the radiation-baked surface, selecting promising samples based on contextual clues, and conducting sophisticated experiments beyond the scope of automated systems. The establishment of even temporary Mars outposts would represent the furthest expansion of human presence in our history and potentially the beginning of humanity's transformation into a multi-planetary species. Beyond the Moon and Mars, robotic missions will continue exploring the outer solar system in unprecedented detail. The Europa Clipper mission, scheduled for launch in 2024, will perform 45 close flybys of Jupiter's ice-covered moon Europa, using instruments including ice-penetrating radar to study the subsurface ocean that may contain twice as much water as all of Earth's oceans combined. Its magnetometer will measure the depth and salinity of this ocean by detecting its influence on Jupiter's magnetic field, while cameras with resolution down to 1 meter per pixel will map the moon's fractured surface in unprecedented detail. Similarly ambitious missions to Saturn's moon Enceladus could sample the water plumes erupting from its south polar region, potentially detecting organic compounds or even biomarkers if life exists in its subsurface ocean. A mission to Neptune and Uranus, the only planets in our solar system not yet orbited by spacecraft, could transform our understanding of these ice giants, which recent exoplanet discoveries suggest may be among the most common types of planets in the galaxy. Sample return missions will increasingly bring extraterrestrial material to Earth for detailed laboratory analysis. NASA and ESA's Mars Sample Return mission aims to retrieve samples collected by the Perseverance rover, while various space agencies have proposed missions to return material from the lunar poles, asteroids, and comets. The scientific value of sample returns lies in the ability to analyze material using instruments too large, complex, or power-hungry for spacecraft, from enormous mass spectrometers to synchrotron beamlines to atom probe tomography. These analyses can determine isotopic ratios with extraordinary precision, identify complex organic compounds, and reveal mineralogical structures at the atomic scale, providing insights impossible through remote sensing alone. Each grain of extraterrestrial material contains a record of the processes that formed it, offering windows into cosmic history from the solar system's birth to the present day. The search for life beyond Earth represents perhaps the most profound scientific question driving future space exploration. Within our solar system, Mars remains a primary focus, with samples being collected specifically for their potential to preserve ancient biosignatures. Future missions may target regions where subsurface brines might support current microbial life. Meanwhile, the ocean worlds of the outer solar system, Europa, Enceladus, and Titan, present environments potentially more habitable than Mars. Europa Clipper will be followed by a proposed Europa lander that could sample surface material for signs of organic compounds that have upwelled from the ocean below. Even more ambitious concepts include cryobots that could melt through kilometers of ice to reach liquid water on Europa or Enceladus, and submarine-like vehicles to explore the hydrocarbon lakes of Titan, where exotic life might use methane as a solvent rather than water. Beyond our solar system, the discovery of thousands of exoplanets has transformed our understanding of planetary systems, revealing that planets are the rule rather than the exception around stars. Future observatories will characterize the atmospheres of potentially habitable worlds, looking for combinations of gases that might indicate biological activity. The simultaneous presence of oxygen and methane, for instance, would suggest biological processes, since these gases would quickly react and disappear without continuous replenishment. More comprehensive biosignature frameworks are being developed, considering factors like atmospheric disequilibrium, where chemicals exist together despite their tendency to react. Surface signatures like the red edge, where vegetation reflects infrared light, and even potential technosignatures if advanced civilizations modify their planets in detectable ways. The discovery of even microbial extraterrestrial life would transform our understanding of biology and our place in the cosmos, suggesting that life might be common throughout the universe rather than exceptionally rare. Propulsion technology represents a crucial frontier for expanding human presence beyond Earth. Chemical rockets, while reliable, are fundamentally limited in their efficiency, making journeys beyond Mars impractically long and expensive. Various advanced propulsion concepts under development could dramatically change this equation. Nuclear thermal propulsion, which uses nuclear reactors to heat propellant, could achieve specific impulses around 900 seconds, double that of chemical rockets, potentially reducing travel time to Mars by half. NASA's Draco project with DARPA aims to test nuclear thermal propulsion in orbit by 2027. Even more ambitious are nuclear pulse propulsion, using controlled nuclear explosions for thrust, and fusion-based systems, which could theoretically achieve a significant fraction of the speed of light if successfully developed. Electric propulsion systems like ion drives offer high efficiency for robotic missions, though their low thrust makes them less suitable for crewed spacecraft needing rapid transit. Perhaps most speculative are concepts like solar sails and beamed propulsion, where spacecraft deploy vast reflective surfaces propelled by sunlight or laser beams from Earth. The breakthrough Starshot initiative proposes using gigawatt laser arrays to accelerate gram-scale spacecraft with light sails to 20% the speed of light, potentially reaching Alpha Centauri within 25 years. While solar and laser sail demonstrations have already flown, scaling to interstellar capabilities would require enormous technological advances. These advanced propulsion systems would transform not just human exploration, but robotic science missions as well. A fusion-powered spacecraft could reach Neptune in less than a year, rather than the 12 years required by Voyager 2. Missions to the gravitational lens point, where the sun's gravity focuses light from distant objects, creating a natural telescope requiring a spacecraft at 550 astronomical units from the sun, would become feasible within a human lifetime. Flyby missions to the nearest stars could return data within a human career span. The infrastructure of space itself may undergo profound changes in coming decades. The plummeting cost of launch services, driven by reusable rocket technology, has already begun democratizing access to space. Commercial space stations may replace or supplement the International Space Station after its planned retirement, with companies already planning independent facilities supporting research, manufacturing, tourism, and potentially film production. These facilities would likely begin in low Earth orbit, but eventually extend to lunar orbit and beyond as transportation costs decrease and space-based industry develops. This trend might eventually enable large-scale industrialization of Earth orbit and beyond. Proposals for space-based solar power would place vast arrays of solar panels in geostationary orbit, beaming energy back to Earth via microwaves and potentially providing clean, continuous power on a massive scale. Asteroid mining represents another potential space industry, accessing precious metals and other resources without environmental impact on Earth. Artificial intelligence and advanced computing will increasingly transform both robotic exploration and scientific analysis. Future spacecraft and rovers will likely possess much greater autonomy than current systems, making decisions without waiting for commands from Earth, crucial for exploring distant worlds where communication delays make real-time control impossible. Future systems might independently identify unusual features, adjust instrument parameters based on initial readings, and redesign their investigation strategies without human intervention. Neural networks trained on terrestrial geology already help identify promising targets on Mars. Future systems might develop novel scientific hypotheses based on their observations. For outer planet missions, where round-trip communication times can exceed many hours, such autonomy becomes not just beneficial, but essential for efficient exploration. Machine learning algorithms already help astronomers sift through petabytes of observational data, identifying patterns that human analysis might miss. Quantum computing, if it fulfills its theoretical promise, could enable simulations of physical and chemical processes far beyond classical computing capabilities. Problems currently intractable for classical supercomputers, like precise molecular dynamics simulations or many-body quantum systems, might become solvable with sufficient quantum bits and error correction. Simulating the quantum mechanical behavior of molecules could revolutionize our understanding of prebiotic chemistry, potentially revealing pathways for life's emergence under various planetary conditions. Similarly, quantum simulation of condensed matter physics might lead to discoveries of room-temperature superconductors or exotic states of matter that could enable technological breakthroughs in energy transmission, propulsion, or sensing. These computational tools won't replace human scientists, but will vastly extend their capabilities, allowing exploration of data spaces and theoretical models of unprecedented complexity. The possibility of human settlement beyond Earth represents perhaps the most profound potential transformation of our species' relationship with the cosmos. While permanent bases on the Moon or Mars might be established in coming decades, self-sustaining colonies independent from Earth would require solving enormous technical challenges, from radiation protection to closed-loop life support systems to artificial gravity on long journeys. Radiation poses a particularly serious threat to long-term habitation beyond Earth's magnetic field, with galactic cosmic rays and solar particle events potentially causing cancer, cardiovascular disease, and central nervous system damage. Life support systems would need to recycle nearly 100% of water, oxygen, and nutrients to achieve independence from Earth resupply. Food production would require significant volumes dedicated to agriculture, either through traditional hydroponics or emerging technologies like cellular agriculture to produce meat and other complex foods without raising animals. Despite these challenges, the advantages of space settlement could be equally profound, accessing resources beyond Earth, ensuring humanity's survival against planetary-scale disasters, and developing new societies and cultures adapted to environments fundamentally different from our evolutionary home. O'Neill cylinders and similar space habitat designs could theoretically support thousands or millions of people in artificial environments throughout the solar system. These rotating habitats, potentially constructed from lunar or asteroid materials, would use centrifugal force to simulate gravity, while their hulls would shield against radiation. While such large-scale habitation remains speculative and distant, Incremental steps in this direction will likely unfold over coming centuries, beginning with scientific outposts that gradually develop greater self-sufficiency and permanence. The search for answers to fundamental cosmic mysteries, dark matter, dark energy, the nature of black hole singularities, quantum gravity, will drive theoretical physics and observational astronomy for generations to come. Future experiments might directly detect dark matter particles using increasingly sensitive detectors, or observe its effects through gravitational lensing with unprecedented precision. Understanding dark energy might come through more accurate measurements of cosmic expansion across time, potentially revealing whether this mysterious force is constant or evolving. The proposed Euclid and Nancy Grace Roman space telescopes will further constrain dark energy models through complementary techniques, including weak gravitational lensing and baryon acoustic oscillations. If dark energy shows any variation over time or across space, these observations might distinguish between competing theories, including a cosmological constant, quintessence fields, or modifications to Einstein's theory of gravity. Gravitational wave observatories might detect echoes from inside black hole event horizons or signals from before the Big Bang, testing theories about information preservation and cosmic origins. While classical general relativity predicts that black holes are perfect absorbers with no internal structure detectable from outside, some quantum gravity theories suggest that information about what falls into a black hole might be preserved in subtle ways, potentially detectable as echoes following black hole merger events. Similarly, certain theories of cosmic inflation predict distinctive patterns in primordial gravitational waves that might be detectable by future observatories, potentially providing a window into the first instance after the Big Bang. These investigations push against the fundamental limits of knowledge we've discussed, yet each incremental advance expands the sphere of human understanding, even if complete knowledge remains perpetually beyond reach. Beyond scientific advancement, space exploration will likely continue transforming human perspective and values in ways difficult to predict. The overview effect, the cognitive shift reported by astronauts upon seeing Earth from space as a fragile, borderless whole, may become a more common experience as more people travel to orbit and beyond. Commercial space tourism, already in its early stages, might eventually make suborbital and orbital experiences accessible to thousands or millions of people. This shift in perspective, from seeing Earth as a collection of nations and territories to experiencing it as a unified living system without visible borders, could potentially influence human values toward greater environmental consciousness and international cooperation. The discovery of extraterrestrial life, even microbial, would likely trigger profound philosophical and religious reconsiderations of humanity's place in the cosmos, potentially leading to both conservative retrenchment and progressive reinterpretation of existing worldviews. The development of self-sustaining communities beyond Earth would create new cultures and perhaps new branches of humanity adapted to different environments. Communities on Mars or in space habitats would develop distinct cultural identities shaped by their unique environmental constraints, limitations on communication with Earth, and selection effects in their founding populations. Over generations, these communities might diverge physiologically as well, whether through natural selection in lower gravity environments, or potentially through deliberate genetic engineering to enhance radiation resistance, bone density maintenance, or other traits advantageous for space habitation. The legal and political relationships between Earth and off-world communities would likely evolve over time, from initial dependence toward increasing autonomy and potentially complete independence as distances and differences grow. The economics and politics of space activities will undergo their own evolution as more nations and private entities develop space capabilities. The current trend toward commercialization seems likely to continue, with private companies taking increasing responsibility for launch services, space stations, and even planetary exploration. Government agencies may increasingly focus on basic research, coordination, and governance, while partnering with commercial entities for implementation. New frameworks for resource utilization and property rights beyond Earth will need development, balancing incentives for commercial development against principles like the non-appropriation provisions of the Outer Space Treaty. International cooperation will remain essential for the largest projects, though competitive and even adversarial relationships will likely persist in some domains. The establishment of lunar and Martian outposts will necessitate new governance frameworks beyond what existing space law provides. The timeline for these developments remains uncertain and contingent on factors difficult to predict, from funding priorities to technological breakthroughs to geopolitical circumstances. Some advances may unfold more rapidly than expected, while others might face unforeseen obstacles. The history of space exploration includes both dramatic leaps, like the 9-year journey from suborbital human spaceflight to the moon landing, and periods of relative stagnation or retrenchment. The coming centuries will likely see similar patterns of acceleration and plateau as various factors align or conflict. Economic considerations will play a major role, with successful commercialization potentially accelerating certain developments while potentially neglecting others with less immediate financial return. Public enthusiasm and political will remain crucial for larger scientific and exploratory endeavors without clear commercial applications. For all the technological marvels and scientific discoveries that await, perhaps the most profound aspect of future space exploration will be its impact on humanity's self-understanding. Each major advance in our cosmic perspective, from the Copernican revolution to the discovery of galaxies beyond our own to the cosmic microwave background, has transformed how we conceptualize our place in the universe. Future discoveries will likely continue this pattern, revealing new layers of cosmic structure and process that challenge our existing frameworks. The search for extraterrestrial life may provide context for understanding life on Earth, not as a unique miracle, but as one expression of a phenomenon that may be widespread throughout the cosmos. Similarly, the potential development of self-sustaining human communities beyond Earth would transform our species' relationship with its home planet, creating new branches of human culture and perhaps new definitions of humanity itself. Throughout this series, we've explored the vast realms of cosmic mystery, from dark matter and dark energy to the multiverse, from black holes to the nature of time, from the Fermi Paradox to the limits of human knowledge. These investigations have revealed a universe far more complex, mysterious, and fascinating than human intuition would suggest. Yet they've also revealed something profound about humanity itself, our remarkable capacity to transcend our evolutionary origins and develop tools, both technological and conceptual, that extend our senses and understanding far beyond their natural limits. The story of cosmic exploration is simultaneously the story of human consciousness gradually awakening to the true nature of its cosmic home. Even as we acknowledge the fundamental limitations that constrain complete knowledge, we can marvel at how far this journey of discovery has already taken us and anticipate with wonder the discoveries that future generations will make. As we look to the stars from our small planet in an ordinary galaxy, we find ourselves at a pivotal moment in our species' history. For the first time, we possess both the understanding of our cosmic context and the technological capability to expand beyond our planetary cradle. The path ahead contains enormous challenges, but equally profound opportunities. The universe we've begun to explore presents more mysteries than we could solve in 1,000 lifetimes, more wonders than we could catalogue in 1,000,000 years. Each answered question reveals new questions. Each discovery illuminates new realms of ignorance. Yet in this endless frontier lies the promise of continued growth in knowledge, capability, and perhaps wisdom. The cosmic journey that began when our ancestors first looked skyward with curiosity continues through us and will extend far beyond our lifetimes, an unbroken chain of inquiry and exploration stretching from humanity's distant past into its unimaginable future. This cosmic perspective offers both humility and inspiration, humility in recognizing our physical insignificance within the vast cosmos, and inspiration in recognizing our privileged role as conscious beings capable of comprehending, however partially, the universe that produced us. We are the universe becoming aware of itself, matter and energy organized into structures complex enough to contemplate their own origins and destiny. In our telescopes and space probes, our mathematical models and scientific theories, the cosmos has developed tools to study itself, to trace its own evolutionary history, to predict its own future. This remarkable recursion, the universe coming to know itself through the consciousness of one of its products, represents a phenomenon potentially as significant as the formation of the first stars or the emergence of life itself. The future of space exploration is not merely the story of technology and discovery, but the continuing evolution of cosmic consciousness through the vehicle of human inquiry and understanding. As we conclude this journey through cosmic mysteries, we recognize that the greatest mystery may be consciousness itself, the capacity that enables all our other investigations, that the universe has organized itself through billions of years of cosmic and biological evolution into entities capable of contemplating the cosmos represents a wonder perhaps exceeding all others we've explored. Whether this capacity exists elsewhere in the universe remains unknown, making humanity's cosmic journey all the more precious and significant. Each discovery, each insight, each new question asked and partially answered adds to a growing edifice of understanding that transcends individual human lives. This collective endeavor, passed from generation to generation and potentially from Earth to other worlds, forms perhaps the most meaningful legacy our species could create, a testament to the remarkable phenomenon of a universe coming to know itself through the adventure of exploration and discovery.